All good? Okay. We still have a little bit, so. Okay, I think we can get started. Okay, we're going to continue covering prefetching. And I have this ambitious 18A numbering over here. Let's see if we finish prefetching today. If we do finish, then we'll start covering simulation. If not, we'll be done with prefetching hopefully today. As I said yesterday, this is such a fundamental topic. If you're going to work on if you're going to work on processor architecture, I think this is the place to work on prefetching in the memory hierarchy. There's also another place which is much harder today, which is control flow handling. I think the headroom in control flow handling is much lower than the headroom in prefetching. Although there is some headroom over there also in branch prediction, for example, especially branch target prediction, etc., for indirect branches. But prefetching has probably much higher headroom given the memory bottleneck. And also, I think it's good to think about prefetching in other contexts, not just processor-centric designs. If you have a memory-centric design, processing near memory, processing using memory, how does prefetching work over there is a relatively unexplored area. And things may change over there. There's still need for prefetching over there because the latencies to access DRAM or whatever memory you're using is still pretty high, I think. Although it's much better than what the processor sees, it's still not as good as what you would like it to be to do processing. So it's good to consider these old ideas or old topics within the context of new constraints always. Okay, that said, we've covered a lot in this agenda that spans 2 days. We've covered a lot of the questions, especially software and hardware prefetching, but we're going to continue with hardware prefetching. Where we stopped was really feedback-directed prefetching. I'm not going to cover that again, but this is incorporating feedback into prefetching decisions so that you can throttle the prefetcher based on how good your prefetcher is doing and based on the availability of resources is really critical to make your prefetcher work well under many conditions. And this is really used in existing processors today. And there needs to be more, like better usage. And this is an area where actually machine learning techniques can help, in my opinion, to modulate how well the prefetcher does. And as I said, you need to tailor this to multicore. Whenever you have multiple threads, throttling a single thread may not work very well, throttling up or down. You really need to take into account what's happening across different threads, interference in the shared resources. And this work takes into account that interference. I'm not going to cover that today. When we talk about multi-core, multiprocessors, we may get back to this sort of issues. Essentially, you need to be prefetching aware in shared resource management. These are some papers on the topic that advance the state of the art, which I'm not going to cover. But I will basically quickly cover some of the issues that happens in multi-core. One issue that we have discussed briefly yesterday was coherence misses, right? Communication misses. When multiple threads are communicating through shared memory, when one thread caches a location and updates it, you will need to invalidate it in another thread's private cache. And this leads to a communication or coherence miss when that thread whose cache is invalidated with that location needs that data again, right? So these sort of communication misses happen a lot, actually. And we're going to cover that more when we talk about multiprocessors. How to prefetch for these is interesting. So for example, one of the issues that happens with multiprocessors that we will discuss is ping-ponging of locks. You actually, one thread acquires the lock, and lock is a shared variable in shared memory. And when you acquire the lock, you need to update the location with some value. And when you update the location, that lock gets invalidated in all of the other processors' caches. Now, when some other processor tries to acquire the same lock, they need to bring that data. So they incur a cache miss in that lock address. So they will need to bring the location to their cache. And when they update it, they will invalidate all of the other caches. So this lock gets this lock travels across many private caches. And this is called ping-ponging of data. In this particular case, lock that protects the shared data. But it's a lock is a shared data itself. Also, you can consider it metadata, of course. But this is actually important. So predicting, for example, which thread will prefetch or will need the lock could be useful after another thread acquires and releases it. So it's good to think about that. It's not an easy problem to handle, but it could be something to handle. And this is not just locks, it's also shared data, right? So you may have a data structure. One thread is modifying one part of the data structure. Another thread is going to modify or read the same part of the data structure later on. And while this thread is modifying this part of the data structure, it will keep it in its own caches. Another thread will need it later on. And whenever it accesses those parts of the data structure, it'll get cache misses. Right? If you can understand the communication patterns between threads, you can actually design a prefetcher that can communicate those data earlier to the thread that will need it later in the future. Later, when we talk about these issues, we will talk about, for example, marshalling the data from one processor to another processor. If you can predict that another processor will need it later on. So that's the prefetching shared data part over here, essentially coherence misses. And this, I think, is a very interesting area, but a very tough way of predicting. And I don't see a whole lot of work recently, actually, in this area. Have you seen a lot of work, Rahul? Yeah, I think it seems like people have forgotten this area a little bit because everybody's so, okay. I think, you know, you can finish the sentence if you want with your prediction, with your prefetching mechanism. But these are really important things. Okay, so prefetching efficiency becomes a lot more important also in multi-core and when you're bandwidth constrained, when you're sharing resources clearly, because your bandwidth is much more precious now, right? A single core may not actually utilize a lot of that bandwidth, but when you have multiple cores or multiple accelerators needing bus bandwidth, it becomes much more precious. So you need to be much more careful in what you prefetch. This is one of the reasons why GPUs don't do a lot of prefetching today, because GPUs, they have, in general, at least in the general common parallel application use cases, you have lots of threads, and these lots of threads generate a lot of requests. And memory bandwidth, I'm not going to say it becomes oversubscribed, but actually memory bandwidth it becomes very precious because a lot of threads use it. And if you add prefetching on top of this, you need to be extremely careful. This doesn't mean that you cannot do it, as we have discussed yesterday, a little bit on bus bandwidth, but you need to be much more careful. Cache space also becomes more valuable, but maybe less valuable than bus bandwidth because there's a lot of cache space people dedicate today, as we have seen in the past. Okay, one of the issues is one core's prefetches interfere with other cores' requests. This leads to cache conflicts at multiple levels, bus contention at multiple levels, and contention at different levels of the DRAM hierarchy, essentially. And as we have discussed yesterday, even if you generate accurate prefetches, those accurate prefetches can actually lead to displacement of some other core's requests from the cache or a delay of some other core's requests in the bus. It could lead to row buffer contention, etc. So it could actually lead to things that are not good, even if you're accurate. So that's the interesting part. And again, I'm not going to go through this, but these particular papers talk about this problem, especially this paper gives examples of how accurate prefetchers can hurt the performance of other cores. And overall, you need to have a mechanism that coordinates the throttling of different prefetchers. Okay, I will not go over this more, as I said. We may get back to it when we talk about multiprocessors because I want to talk about some other things. But if you have questions right now, we can talk about it. So this work actually designs a DRAM controller. I have some backup slides if you're interested, but the paper is also out there that considers prefetch accuracy. How should you schedule requests between prefetches and demands if you have a memory controller? And this has been an outstanding problem for a very long time. If your memory controller is aware of which request is a prefetch request, which request is a demand request, there are clearly two policies you can do. Prefetches and demands can be considered equal. This is a static policy, or demands are always prioritized over prefetches. Right? These are static policies. You may say it always prioritize demands over prefetches, but it turns out that's not a good policy overall. There are cases where you want to prioritize prefetches over demands, especially when prefetches are accurate. So if your prefetch is accurate, you may consider it almost as an early demand, right? It's good to think about it that way. If it's inaccurate, and if you know that, if you have good confidence that it's likely inaccurate, you may want to consider it as a demand. So the idea, one of the ideas in this work is to say, communicate the accuracy of the prefetches to the memory controller. And if the prefetch is accurate, prioritize it over demands or make it as equal as demands. This has some benefits. For example, as we discussed briefly yesterday, one of the benefits is if the row buffer is open for that prefetch row, you could exploit the row buffer locality, as opposed to changing the row buffer to access a demand and then later changing the row buffer so that you access the prefetch requests. Okay, so keeping the row buffer open for accurate prefetch is actually, in general, a very good idea, as opposed to switching between demands and prefetches, demands and accurate prefetches. There are more nuances over here that are interesting to consider, and I think there needs to be more consideration of these. Okay, there's more works that I'm not going to talk about. Cache management is actually also interesting. There are a lot of ideas here that I'm actually not going to cover. And we have actually looked at prefetching in GPUs, and in some cases, actually, this could be useful, especially if you're considering row buffer locality. This is again important. If you consider row buffer locality and do the prefetching carefully so that you maximize row buffer locality as opposed to hurting bandwidth by switching the row buffer, then you can actually get benefits. Any questions? Okay, we will have lectures on multiprocessors, bottleneck acceleration later on. So we will talk about that, cache coherence and consistency, which is different, but we will talk about that. Okay, now let me cover some advanced prefetching ideas, self-optimizing prefetchers. We had covered self-optimizing memory controllers, if you remember, reinforcement learning-based memory controllers. This is going to be somewhat similar, except it will be adapted to the prefetching context. This is Rahul's work. Maybe he can cover it in more detail later, but this is old work right now. It's been 3 years. 3 years is pretty old in technology, as you know. But sometimes in technology, people forget that technology has been around for longer, and they forget what has happened in 1990s, 2000s, and they restart from 2020 or so. So it's not that old in that sense. So it still is considered by some people, but it's good to think about the history. I'm going to give you some history later on from 1960s, 70s, etc. in prefetching. Okay, so what is self-optimizing prefetchers? You may have guessed it. It's essentially using reinforcement learning to do offset-based prefetching. We've covered reinforcement learning, but just to jog your memory, it's an algorithmic approach that enables an agent to decide which action is, let's say, good, useful to take given a situation, so that you can maximize a reward function. So you have an agent that interacts with an environment, and the agent observes the state of the environment, and it takes an action, and it gets a reward based on its action. Reward can be nothing, basically. It's a zero reward also, right? You take an action, you don't get a reward immediately, but over time, you may actually get a reward, as we have discussed with memory scheduling. And basically, the agent stores, this is a particular form of reinforcement learning, Q learning, where the agent stores Q values for every state action pair. Of course, every is, and overdoing it perhaps potentially, right? It's really state action pairs. It could be quantized, it could be generalized, etc. We've discussed this when we talked about memory control. So the same things happen over here as well. But basically, in the ideal case, you try to figure out Q value specifies the expected return for taking an action in a given state. And your goal is to select the action that provides the highest Q value, and also update the Q values accordingly, so that whenever you observe a state, whenever you're in a given state, you decide to take the action that will maximize the reward, whether it's a long-term reward or short-term reward. You can make the reward, of course, long-term or short-term, depending on the update function you have for the Q values. Okay, that's the general reinforcement learning. I think you have read the paper, Self-Optimizing Memory Controllers. How many people have read that paper so far? Okay, some people are raising hands. That's good. I don't remember if it was a required paper, but it's fine. I think you can read it anytime. So PFIA, essentially, this is the prefetcher that Rahul developed that formulates prefetching as a reinforcement learning problem. So agents is the prefetcher, environment is essentially the processor and memory subsystem, but it could be broader also. And state is the features of a memory request to address A. So we're going to now specialize things a little bit. As you can see, for example, the program counter that generated the request to address A could be the state. And then action is, again, specialized to the offset-based prefetching. We're going to try to decide what offset to prefetch based from address A. It could be multiple offsets also, right? Depending on what prefetches you generate. But now, once you take that action, you will get a reward. And based on the reward, you would update the tables of the reinforcement learning-based prefetcher so that you find the best offsets that will lead to the best reward values given a reward function. Hopefully this makes sense, right? This is clearly a constrained version of application of reinforcement learning to prefetching, because we've seen a lot of different types of prefetchers so far. And you can say this is one type of prefetcher, right? Clearly that's the case. And this may not be the best, let's say, benefits that you would get by applying reinforcement learning to prefetching. There may be other ways of actually doing this, right, Rahul? And you can actually get even better benefits. So there's a lot of room for, I think, improvement and creativity over here. But even with this constrained application, you will see that there are benefits that you can get compared to state-of-the-art prefetchers, many of which we have not actually covered, but you can read about. But essentially, they work. They operate based on similar principles. You can determine the offset to prefetch, right? One way of determining the offset to prefetch is really stride. We have seen that, right? Another way is really patterns in stride, right? Multiple strides, correlation, a delta correlation prefetcher, deltas and strides, right? So it's not that different from those approaches. You could replace, for example, offsets with deltas, right? Multiple deltas. So I think there's a lot of room for improvement over here. That's my whole point over here, even though we see improvements in this case. So the question, of course, as you have seen with reinforcement learning previously, when it was applied to memory controllers, the question always is, what is state? What state features you examine? What are the actions you take? And what is the reward function? And usually reward function is the hardest one. State, as we have discussed last time, you can actually explore that state space using feature selection processes. And I think there are dynamic ways of exploring it, although they could be expensive in hardware. But the exploration here is, again, using feature selection. But in this case, we look at a k-dimensional vector of features. And features could be control flow features, data flow features, and actually anything that you observe. But I think Rahul looked at a bunch of different things that all of them are listed in the paper. But control flow examples could be the program counter that led to this address. Think about instruction-based stride prefetching that we discussed yesterday, right? Clearly, that's a feature that was important for instruction-based stride prefetching. It could be the last seen branch program counter, which was not taken into account in the previous mechanisms that we discussed yesterday, at least explicitly. Implicitly, you could take that into account, of course, right? When you actually, so one mechanism I didn't discuss was, for example, to get ahead, instruction program counter-based prefetchers usually do look ahead program counters, and that kind of implicitly may take into account branch PCs. Now you can actually feed this information explicitly into a table that will give you a prediction. Or you could actually be more sophisticated. You could look at last 3 program counters that you have seen, right? Or some sort of path information in the program. So essentially, the idea is to correlate or incorporate information about the control flow that the program is taking to the prefetcher, so that hopefully the prefetcher makes a better decision in terms of selecting the offset. This could be other things like return addresses, call stack that you have seen, many other things essentially. It could be also communicated through the software, as we may see later on. But although in this case, this is purely hardware solution at this point. I'm giving you some thoughts so that maybe people who are excited about doing, generating creative ideas can do better. That's always the goal, right? Okay, so there could be also data flow features like cache block address. What is the address of this cache block that you're addressing, looked at? What is the address of the last few cache blocks, for example? What is the physical page number, which could be different from the virtual address, clearly. What is the delta between the last seen consecutive addresses, right? What is the delta between many consecutive addresses that you've seen in the recent past? Last 4 deltas, for example. You can imagine many other things over here also, right? You could also potentially try to incorporate other states that are not control flow, not data flow, but really the state information, right? Maybe you can talk about that more later. So that's state. And this, you come up with these examples, and then you do feature selection like we've done in the past. Hopefully you select a small number of features than 200 or so. Because clearly, if you have more features, it becomes more difficult to not only just train online, but also it becomes more expensive to build the hardware to do the training. And also prediction, not just training. Okay, so what is action? In this case, we restrain the actions a lot. Given a demand access to address A, the action is to select a prefetch offset O, essentially. What is the offset that you're going to prefetch from address A? And we're going to constrain it even more. The action space is constrained to 127 actions in the range minus 63 to plus 63. And the reason here is we're going to prefetch for a machine with 4 kilobyte page and 64 byte cache line, right? A zero offset means no prefetch is generated. So there's an option to generate no prefetch. For example, if the prefetching is going to be somewhat not going to give you a positive reward later on, the prefetcher can automatically decide to choose offset 0, right? That's a nice option. We had this, for example, also in the memory scheduler, right? We had a no-op action in the memory scheduler. Memory scheduler can decide to choose no-op, issue no valid command, because maybe you just want to keep the row buffer open for some time and not schedule any request, right? And then Rahul likes this pruning. I don't like it as much, but then you prune the action space by some design space exploration to make it even, let's say, less flexible. So I think you come up with, in the end, how many? 17, 16 offsets? 16 offsets, which means that you cannot prefetch some offsets if you actually do that, if you actually use this as your prefetcher. So you can see that there's room for improvement. Okay, but even with this, you'll get good benefits. So it's not an easy design, I should say. I think you to make it, let's say, easier to integrate the existing implementations, you need to come up with constraints like this. Okay, so what is reward? Reward is also not easy. This defines the objective of the prefetcher. And in this particular case, we want to encapsulate two metrics. One is prefetch usefulness, whether it's accurate, whether it's late, whether it's out of page. In this case, we're not doing prefetching beyond the physical page boundary, essentially. But that's another topic that could be interesting to look at, like how do you prefetch across pages? It clearly leads to some system level issues, right? When the prefetcher generates a page fault, what do you do, etc. It's good to think about. And then there's also system level feedback that's directly taken into account in the reward, which is a bit different from what we have done with throttling last time, right? With throttling, we designed the prefetching algorithm. We decided what to prefetch, and then we decided to throttle the prefetcher based on what's happening, right? But you could also incorporate system level feedback into the prefetching rewards. For example, memory bandwidth usage, cache pollution, energy. In this particular case, we look at memory bandwidth usage as a system level feedback. I should also say that accuracy is also similar, right? Accuracy was kind of like an afterthought in all of the previous prefetching algorithms. We never designed an algorithm say, incorporating accuracy as a fundamental input to the algorithm itself. It was always kind of like an afterthought where you have that algorithm. This algorithm generates a bunch of prefetching addresses. We just throttle it up or down. Right? Here, the reward function encapsulates all of those things that we could encapsulate as part of the throttling mechanism. Okay, so let's take a look at this reward specification because it becomes interesting over here. It also kind of gets back to the discussion we had about metrics yesterday. Clearly, in this particular accuracy, timeliness, coverage are important. And you get different rewards for a prefetch that's accurate and timely versus a prefetch that's accurate but late versus a prefetch that loses coverage versus for some definition of that in the paper or Asterhul. Or it's a prefetch that's inaccurate, but inaccurate under low memory bandwidth usage versus high memory bandwidth usage, because these are different scenarios, right? If you're inaccurate and the system needs that memory bandwidth, that's probably a bad thing. Worse thing than if you're inaccurate when the system doesn't need as much bandwidth in memory. And then there's no prefetch. Again, you're not, you didn't prefetch, but memory bandwidth usage was low versus you didn't prefetch, but the memory usage, bandwidth usage was high. Basically, you get different reward values for these different levels. I think 7 different reward values, as you can see. And again, you can set the values at design time via design space exploration. This could potentially be done dynamically also, but it's probably harder to do dynamically. Is it possible? Yeah. Yeah, everything is possible. It just takes effort and time and cost. Okay. And this could also be, I think one thing that's really interesting in this sort of prefetcher is these could be customized these doesn't need to be hard-coded, basically. You design the hardware. These could be configurable registers. And you can configure these registers for rewards, potentially state also, actually, but it was not explored in this paper, but for rewards based on what kind of workload is executing, what kind of requirements you have for the workload. For example, if you know that your workload is extremely bandwidth intensive and cannot tolerate inaccurate prefetchers, you can configure these reward values such that it penalizes inaccurate prefetches much more than you otherwise would. So it's good to think about that. That's one of the advantages of having configurable prefetchers. And I think this is one example of a configurable prefetcher. Making this more configurable is actually a good idea going into the future. Yes?
Is it the point to actually not have to deal with the prefetcher?
Yeah. Well, in this case, it's learning the offsets, right? The question is, what do you learn? Here, it's learning the offsets. Yes, you may also try to learn the rewards, but that's a much harder problem, I think, than learning the offsets. It'd be nice, of course. Yes, I agree. If someone comes with a prefetcher that learns all of these rewards, that's even better. It could be eventually, right? You could potentially make it learnable, but that's a contribution by itself. Yes, I think it could be important. Yes, based on not just workload, but the dynamic system configuration, the goals of the user. I think all of those could be inputs to tweak the rewards, right? Yeah, I think the ideal goal is really user not doing anything and the prefetcher happily learning, but we're not there yet, at least not with this work. Okay, so let's take a look at some example reward configurations that I think design space exploration came up with. If you want to, for example, generate accurate prefetches while taking bandwidth-aware prefetch decisions, this is one reward configuration. For example, you prioritize the accurate prefetches. Accurate and timely prefetches get a positive reward. Accurate and late prefetches get a less positive reward. No prefetching gets somewhat negative reward, especially, yeah. And then inaccurate prefetches get much more negative rewards, as you can see. Okay, you can try to justify some of these. Maybe not all of them are fully justifiable. Maybe Rahul can justify it, but you obtain this through automatic design space exploration, right? Yes, a lot of them make sense. So basically, this reward configuration generates a prefetcher that prefers to generate accurate prefetches, and it also prefers not to prefetch if memory bandwidth usage is low in general. But if the memory bandwidth usage is high, you get penalized for inaccurate prefetch a lot. Okay, so let's take a look at, I think I already said this. Yes, that's the third thing over here. But if you are actually very much intolerant of inaccuracy because of whatever reason, your memory bandwidth usage or cache pollution, or you know your workload, you may actually come up with a reward configuration that looks more like this. In this particular case, you still prefer to generate accurate prefetches. Those rewards are high. No prefetching rewards are okay, I guess. You prefer not to prefetch, but you highly prefer not to perform any inaccurate prefetches. Right? So these rewards are very, very negative, as you can see. So this could be a configuration for some workloads that are very bandwidth intensive. As we've discussed yesterday, server class processors, for example, there's this myth, which is based on some profiling, etc., that you should turn off all the prefetchers in your server class processors. I don't think that's exactly true. You should be careful. But one of the reasons is you have very high bandwidth usage in some of these applications over there. Yeah, bandwidth sensitive workloads, as we will see a little bit, like graph processing workloads. Some of, as we have discussed in many lectures, they're quite bandwidth sensitive. So I think one of the advantages of this sort of prefetch, as I said, is you can change the objective. You can customize it without changing the hardware, just by programming the prefetcher. And this is another goal, I think, going into the future. We talked about programmable memory controllers, configurable memory controllers. I think we really want these hardware pieces to be more and more programmable going into the future so that we adapt to the workloads much better. Right? That's the idea over here. Okay, so let me give you some results. These are essentially, this is the basic PTX configuration that we're going to use to look at the results. We have only two features here. And then we have 16 prefetch offsets, as we have discussed, based on some customization. For example, you don't prefetch minus 55, right? It's gone. Maybe that doesn't happen in workloads. That's why it was customized out. Is that correct? Yeah. And then the rewards are here also. Okay, there's more detailed overview, but I don't really want to get into the implementation right now because we didn't really get into the implementation of many prefetchers. But essentially, what you need to do is you need to evaluate what happened to your prefetches so that you can update these Q value tables, right? Q value stores. And whenever you have a demand request, you generate the state vector associated with the demand request, which takes into account these features that I go back on. Basically generate the state vector. You index your Q value store, and that Q value store gives essentially for all of the possible actions, essentially offset values, you get different Q values, and then you decide which one provides you the maximum Q value, and you generate the prefetch for that one, for that offset. You could again choose multiple offsets, right? You chose one offset here, right? Or did you choose multiple? Or did you vary? Yeah, you can essentially choose multiple offsets. And this is one of the reasons Rahul limited the offset values, because if you want to choose from 128 offsets, that's much more expensive than choosing 16 offsets, right? And these offsets, if you mispredict one offset, you're not going to get it half right in a sense, right? Assuming you're accurate, you really want to get the offset because this is a cache block that you're trying to generate a prefetch for. So these are the real hardware implementation issues that you need to deal with, essentially. There's a lower level hardware implementation that is in the paper and other slides, but I'm not going to cover that. Okay, so let's take a look at the performance of this. So these are some old prefetchers. We're going to vary the number of cores. And this is the speed up that you get over no prefetching. You can see that different prefetchers are reasonably good. They give good speed up. Of course, as number of cores increases, the speed ups reduce because the bandwidth contention increases. And this is what Pythia gives you, which looks pretty good. I don't know what this 3% refers to. Yeah, this is 3% is basically compared to the best prefetcher with 1 core. And this is compared to the best prefetcher with 12 cores. So you can see that the performance improvement Pythia gets is, I guess, reasonable. You may say this is small, but these are actually big numbers because we're talking about single core over here. And this is also general purpose. We're not customizing to the workload. Okay, so that's one. The more interesting plot maybe is this, which is what happens if you actually limit the memory bandwidth, memory transactions per second over here from 100, which is very low, to 12,800, which is very generous. I think this is 1 core, right? Yes, this is a single core. A single core has basically limited memory bandwidth versus very ample memory bandwidth. And you can see that some of these actually map to real systems today. I guess baseline is not a real system. Baseline is generous, basically. Is that correct? Okay. So you can see that some real systems actually have very low memory bandwidth per core. And you can see Pythia is actually outperforms the previous prefetchers at all memory bandwidth points, which is actually good, which kind of shows that this is more bandwidth frugal in terms of its prefetching, and more analysis in the paper in terms of accuracy, etc. Does that sound good? Okay. Okay, those are the numbers you can take a look at. This is also interesting, I think, because if you look at the low memory bandwidth point, this is essentially why people turn off prefetchers at low memory bandwidth points. If you have very limited memory bandwidth, you can see that these previous prefetchers, which we have not covered, but they operate on offset-based prefetching, etc., spatial prefetching principles, they all lose performance on average. And Pythia somehow doesn't lose performance, but it doesn't gain performance also, as you can see. So there's a good reason to not do prefetching when your memory bandwidth is very limited. And this is one of the reasons why GPUs in general stay away from prefetching today, because their memory bandwidth availability for a given core is very small, because overall memory bandwidth is, even though overall memory bandwidth may be very high, it's highly utilized by many cores. Okay. Okay. So this is an example of customization. So if you actually use the customized values that I showed you earlier, that are essentially very conservative, that try to preserve bandwidth, that try to penalize inaccurate prefetches in the reward function, and you use Pythia, basic Pythia versus optimized Pythia, which is the orange bars, on graph workloads, you get a lot higher performance improvements. In some cases, for example, in breadth first search, you get close to 8% performance improvement. So you can see that customizing a little bit, not perfectly, of course, to the workload buys you more performance. Make sense? Because this workload is quite bandwidth intensive. I'm actually curious, if you apply these values to general, all of the workloads, what do you get? So you lose actually on the other workloads, right? So that's the interesting part. You should also do the other study, right? Which is the control study. So you use this conservative PTA, which is the orange bar over here, whose reward values are quite negative for inaccurate prefetches, and you use it across all of the other workloads, then they lose performance compared to basic PTA. Yes?
Are the individual orange bars
Yeah, I think the answer is no. It's one optimized version. Basically, the reward values that I showed you for conservative PTA. Yes. You could actually do even more, of course, but then it becomes overfitting a little bit, in a sense, right? Okay. Okay. I think we've discussed this. So the overhead of this comes at an overhead still. So the overhead is 25 kilobytes, which is not small, but which is not bad also. I think later work reduced this overhead significantly. I'm going to briefly mention that. Okay, you can read it if you're interested. And there's clearly overhead that comes with it. And I think this HDL is available, right, online. So if you're interested, you can build on this with both simulation and HDL. All of this is open source. And you can talk to Rahul for more, or you can watch his presentation. Anything you want to add, Rahul? Mm-hmm. Yeah. Yeah, yeah, I absolutely agree. I think there's a lot more to do in this area. Not just tweaking PTA itself, but figuring out how to apply reinforcement learning in a much better way or much more, like we've already discussed some of the issues, right? In a way that would actually gain even more performance, for example. But I'll let you think about that. I think this book I kind of recommended in the last lecture, but maybe I didn't put up the book itself. This is actually a very nice book that covers a lot of reinforcement learning principles. I know reinforcement learning is not as, let's say, sexy as some of the other learning that people are thinking extremely important. But I think reinforcement learning is actually quite, how should I say it? In a sense, its principles are actually quite, at multiple levels, similar to how part of nature operates, right? As we have discussed with memory controllers, this is very basic. And in fact, some psychologists have argued that reinforcement learning is the only principle in which nature operates. B.F. Skinner, if you know B.F. Skinner, this guy is actually a very famous psychologist, and he is kind of the father of reinforcement learning, at least academic father, let's say. And he trained these pigeons who would do a lot of things with reinforcement learning. Maybe he was a bit extreme in his views about reinforcement learning, but it's always good to have some extreme views that push the boundaries. So I'd recommend looking at this book. It covers a lot of other things in reinforcement learning. And this latest edition of the book is actually includes reinforcement learning based memory controllers also, as you can see, as one of the applications. So after these guys read our paper, they said, oh, this looks like a very nice application. And they put it in there in the next edition of the book. I remember reading older editions of the book a long time ago. And another nice thing about this book is it's completely online. So you don't need to fork out $100 for it. I think these publishers are making crazy amounts of unnecessary money out of publishing without really giving it to the authors. Okay. If they were giving it to the authors, that would be a different thing, right? Because who really created the value over here is a good question. Is it the distributor or the person who actually put the intellectual effort to make this happen? Okay, any questions? Otherwise, we're going to cover something else, slightly different. I consider this as another form of prefetching, but maybe Rahul considers it different. We may have a discussion. But it's a kind of different form of prefetching. So basically, can we do better? Can we do better is always a good question. I think maybe I'll go through this. Basically, we're going to talk about off-chip load prediction. Essentially, we've already discussed off-chip load requests. They block the reorder buffer. They limit performance. While I'm at this slide, I should also say that maybe there are some other metrics that should be put into the reward functions, right? As we discussed yesterday, the stall time reduction due to prefetching. If you can somehow do that, I think that could be very interesting. But essentially, these limit performance. Traditional solutions, prefetchers, we've discussed. Caches, we've discussed. These are the two major ones, but clearly we've discussed other things like multi-threading and out-of-order execution. They all have their downsides in the end. You could add more threads, more hardware, and we've discussed that it doesn't improve performance of a single thread. Out-of-order execution is more hardware again. It does improve the performance of a single thread, but you hit diminishing returns as you keep increasing the size of the out-of-order execution window, as we will see in a later work also. So even if you even if you use, let's say, state-of-the-art prefetchers, implementable prefetchers, let's say, many loads still go off chip. You can prefetch maybe 50% of them. Depends on the workload, of course, but on average, let's say. And 50% still go off chip, even with a state-of-the-art prefetcher. These are Rahul's results, so he's responsible for, for explaining it to you if you have questions. And 70% of them block the reorder buffer. Meaning, because these are long latency requests, they eventually become the head of the reorder buffer and they stop instruction retirements, right? So let's take a look at this. One of the issues that we have not talked as much about, but still it's within the boundary of prefetching, is on-chip cache access latency. We've talked about the main memory access latency. To cover for or to reduce the main memory access latency, people have been building longer latency on-chip cache hierarchies. And based on some calculations, essentially, if you want to access main memory today, you need to go through L1, L2, last level cache, and if you find out that you missed the last level cache, then you access main memory. Right? So if you're going to access main memory, what happens is your access time is actually much longer than the main memory access. This is good to think about. It's one of the issues with, I think, from my perspective, a processor-centric paradigm, right? Because you're so processor-centric and you're not memory-centric, we've designed these processors that go through levels and levels and levels of cache hierarchies to eventually get to main memory. But if you actually somehow figure out that you need to get to main memory, you may want to really bypass all of those accesses, right, to the cache. Still processor-centric, but maybe better, right? If you can somehow parallelize the access to the cache hierarchy with the main memory access, you can save a bunch of cycles. Now, this sounds good. Let's do it for every request. Every load, let's access the cache hierarchy. Let's also send a request to the memory controller, start the main memory access. Now sounds bad, right? Because if you send every single load to the main memory, then you need a huge amount of bandwidth that nobody's going to afford today. Now, doing that inside the memory chip is a very different thing. Because inside the memory chip, you have a lot more bandwidth. So that's what memory-centric computing is. You send every load, okay, every load, for some definition of every load, right? Some tasks, let's say. Every load in some tasks inside the memory chip. Then you can exploit the parallelism inside the memory chip. You can exploit the high internal bandwidth, lower latency inside the memory chip. But if you're processor-centric, and if you're actually going through this interconnect that's very bandwidth bottlenecked, and sending every load to main memory is not a good idea. So the goal is to actually get the benefits of this huge latency reduction, 40% with some calculations, without sending every load. Basically, what you really want to do, what I just showed you, show in this picture, the loads for which you want to really do this for are the loads that are going to miss the on-chip memory cache, on-chip cache hierarchy. If you can somehow predict that a load is not going to be in L1, L2, or LLC, you're not going to find on-chip in some way, then start the main memory access right away. That's the idea over here. Then the question is, how do you predict that? Okay, before we get to that, this is just some data showing that on-chip cache sizes are increasing, and hit latencies of caches are also increasing, as you can see. This is old data. I think this is more Rahul's data recently. On-chip cache sizes, L2 size. These are L2 sizes. This doesn't even include the L3 sizes. Why don't you have L3? It's not on chip anymore. Okay. Okay, I see. Okay, yeah, but trend may not be important. Okay, I'll get back to my question. But you can see that L2 cache sizes are increasing, and I think these are mostly private or semi-private, at least shared between a cluster, of course, depending on the architecture. But the access times are also increasing. But L3 cache is much larger, and its access latency is maybe 50 to 70 to 80 cycles, right, today. Is that correct? Maybe even higher? At least, okay. I've seen 80 also. Okay. Okay, so basically, you have actually a lot of time spent on the on-chip hierarchy. And the idea here is, as I said, remove the on-chip cache access latency from the critical path of loads that are going to go off-chip. And this is why your whole developed Hermes. The idea is to predict which loads are likely to go off-chip and start fetching data directly from main memory while concurrently accessing the cache hierarchy to verify that you're actually going to go off-chip. That's the idea. It's a very simple idea. That's good. The key is really how to predict over here. So the prediction mechanism over here is Perceptron based. You may have seen that in earlier branch prediction lectures that you may have had with me, like the digital design and computer architecture. Perceptron is really a very simple, I don't want to even call it a neural network, but let's call it a neuron. Essentially, it has some weights and it takes some inputs. It multiplies the inputs with the weights, and it decides whether the output is greater than some threshold. That's the idea, right? And the neuron fires if it's greater than the threshold. That's the theory in the end, right? It's the most basic form of an artificial neuron, I would say. And we're going to train this neuron, set the weights accordingly based on some features, and based on the calculation, the weight input multiplication, if that's greater than threshold, we will predict that the load will go off chip or stay on chip. That's the idea. Now, I'm not going to go through all of the training, etc., but you're going to use multiple program context information. I'm going to show you some examples. You can read the paper. You will read the paper for more detail, I think. But this is actually a nice way of thinking about or formulating the off-chip prediction problem, right? Okay, let's take a look at how this works a little bit. So in the baseline, as I said, you go through the on-chip cache hierarchy, and you decide the load that the address you're looking for is not on chip. So you start an access to main memory. And your processor is stalled at some point. It could be stalled while you're going through the on-chip cache hierarchy also, right? It depends on where, how old is your instruction, let's say, in the instruction window. Now, in Hermes, we're going to consult a predictor, Perceptron-based off-chip load predictor. And this off-chip load-based predictor will predict whether this load instruction is going to be present in the on-chip cache hierarchy or absent on the on-chip cache hierarchy. If it's absent, we will issue a request directly to the memory controller, which clearly will take some time. And you need a path to the memory controller, direct path to the memory controller, which usually doesn't exist in processors, but it should exist, I think. It could exist depending on your design, how monolithic your design is. Yeah. There are a lot of issues with processor design today. It's not just, but you can see that going through this hierarchy directly is not great if you want to access the main memory directly, right? And one of the issues actually why, okay, I'll go back to some logistic issues in companies. So what happens in companies is usually someone designs the core, and that someone usually also designs the L1 cache. So L1 cache is kind of integrated into the core. It's part of the same team, maybe not exactly the same someone. But once you go outside L1, they don't know what's going on. Don't ask that team. That team is responsible for the on-core, let's say, or outside L1, L2, L3, maybe on-chip interconnect. Once you go outside that, memory controller or some other team is responsible. And these teams usually don't talk to each other. Now, if you want to add a path that spans all of them, this is a very radical path, right? It's not a radical path. I just put it over there. So it's good to think about this, right? This siloization of different parts, even in a single processor. We're not even talking about the whole system, right? Clearly, there's a siloization between memory and processor. But even if you look at a single processor, there's a siloization of components. And usually people don't talk to each other. It's very difficult to implement things that communicate from the core to the L2 cache, or whatever your boundary is between the core and the uncore, let's say. Right? Okay, so it's good to think about this. This is partly human nature, partly for efficiency purposes. You design abstraction levels, and you are within that abstraction level, and outside that abstraction level, you have a clear interface, hopefully, to the uncore. And if someone wants to change that interface, your first reaction is get out. That's the mindset. And here we're kind of changing the interface. Although it may be very reasonable, it may take a long time to change this interface, even with a single company. We're talking about a single company right now. Now, take this picture, apply it to many companies, processor, memory, then you see how difficult things are to change in the bigger ecosystem, the memory interface, for example. We've been talking about that earlier. So it's much, much more difficult. Even with a single company, I've observed this many, many times, difficult to do. So research takes a long time to actually get adopted. Even though it may be a great idea, it may take a long, long time. It may never have happened also. That doesn't mean that it's not good research. It's still good, impactful research because it really stirs the pot at the very least. And it basically pushes people in the right direction, right? Like I'm giving you the example of subarray level parallelism. If this is difficult to do, subarray level parallelism is thousands of times more difficult to do. Okay. It's good that we have RowHammer solutions today. Because that took much faster than many, many other things, as you can imagine. Okay, going back, popping the stack. Essentially, if this predictor predicts that this data that's requested by this load, this address that's requested by this load is not present in the caches, it will inject a request over here. And this request will wait. Well, okay. And it will basically, sorry, I kind of didn't animate this very nicely, I guess. You have an animation over here. Maybe it got animated while I'm talking. I'm not going to press the button. I usually dislike this sort of animation, but Rahul likes them, so what? Yeah, so it takes a long time. He's supposed to be talking over here. Yeah, let's see. And main memory responds, as you can see, and this guy over here waits until there's confirmation, right? And then it really loads the caches. Okay, so when you get the confirmation over here, you basically bring the data in. Okay, and then you save a bunch of cycles, as you can see. Okay, that sounds good. And then you, based on what you have done, you can train your predictor because you know exactly, once you looked up the cache hierarchy, you know exactly whether your off-chip load predictor made the right decision or the wrong decision, right? It's a binary decision. It's not, in that sense, it's not as difficult as prefetching, and certainly not as difficult as memory control. Memory control is much more difficult than prefetching. And prefetching, general offset-based prefetching, is much more difficult than this prediction because here the difference is a binary prediction, whether it's on chip or off chip, right? So you can train it nicely and cleanly in this case. And that's one of the reasons why Perceptron actually is easier to implement. Okay, so again, I will not go through the details of implementation, but there's a, the design of this actually looks kind of like the multi-feature based perceptrons that we kind of use sometimes in processors, right? Essentially, you have a bunch of features. Each feature has its own weight table. And each weight table stores the correlation between the feature value that you see and whether that feature value indicates this should go off chip. This load is off chip or on chip. So a feature value could be, again, a lot of things that we've discussed. It could be the program counter. It could be the program counter plus offset. You could also use the branch, last branch address. You could do anything again. You could have data flow, control flow features. And for that, read the paper for more detail. In fact, I think all of this is open source, right? Okay, and then to predict, you use a bunch of table lookups, addition and comparison. This is just to show you that it's actually not that expensive to do perceptrons, because perceptrons are not as intensive as, let's say, reinforcement learning, Q learning based reinforcement learning, which is not as intensive as deep neural networks in general, which is not as intensive as transformers, etc. You could actually have that hierarchy over there. So you basically extract some features based on the load request. You index, you do some hashing based on the feature values, and you index each weight table, and you get the weights out, and then you sum the weights, and then you compare them to an activation threshold. And if you pass the activation threshold, then you predict that the load will go off chip. Okay. And then after some point, you get the feedback from the cache hierarchy saying you did the wrong thing. That's the X over here. So this really shouldn't have been activated. So you go back and retrain the particular weights that you have used. Makes sense? So you clearly need to recreate this features again when you need to update. This is positive reinforcement. This negative reinforcement, and then you could also do positive reinforcement. Although I kind of abused the term reinforcement over here. Okay. Anyway, so hopefully that's clear. Okay, let's take a look at the improvement this provides. So we're going to look at Hermes alone, Pythia alone, and a bunch of other things later. But if you look at this, Hermes actually provides, on average, less performance improvement than Pythia. But it's also doing something different, right? They could be combined in the end. But I think another thing to consider is the performance benefits come at much lower cost. The storage overhead of this Perceptron is much lower than the storage overhead of Q-learning with Pythia. But of course, they could be combined, as you may have guessed. This may be one way of combining them. You just combine them, right? So there's no, usually sometimes when you combine things, you may need to be careful, right? Because they may be stepping in on each other's toes, right? For example, when you combine out-of-order execution with a memory scheduler, like we have seen, sometimes a memory scheduler may revert the memory level parallelism benefits of out-of-order execution. And we've kind of tried to solve that problem in PAR-BS. Parallelism over batch scheduling recognized it as a problem and said, okay, you should really combine these things more carefully, right? Here, I think there was no need to do something careful, although if you do something careful, maybe you'll get something better. That's also good to think about. But without doing anything, let's say, careful, just putting them together, you get higher benefits than either of them, which is good. Okay, so and the main reason is they're really targeting different things, although there could be some overlap between them, right? Okay, and this is another result which shows what happens if you combine realistic Pythia with ideal Hermes. Ideal Hermes means your predictions are always correct. Whenever you get a load, you know for sure whether you should go off chip or on chip. So there's still some headroom, as you can see, in terms of performance, but surprisingly not too much headroom. Why is there not that much headroom? Mm-hmm. Yeah, maybe in these workloads, there's not that much headroom, right? Maybe some other workloads will have a lot more headroom. Yeah, that's true, yes. In multicore, actually, there's a lot more headroom. This is single core. You should always look at multicore. Okay, there's another interesting thing over here. This is the increase in memory requests. Even though Pythia is actually a relatively frugal hardware prefetcher, Hermes is even more frugal if you look at this picture. So the increase that Hermes has in memory requests is about 5%, 5.5%. Pythia actually increases them much more significantly, although it provides higher benefits also. And if you combine them, essentially you get somewhat of a linear increase, similar to what Hermes would do without prefetching. Okay. So I think Rahul summarized this as, for every 1% performance benefit, Pythia increased memory request by 2%. Hermes on top of Pythia increased memory request by 1%. Hermes alone is actually even more frugal. So it's good to think about that. It's bandwidth efficient, essentially, compared to even an efficient prefetcher like Pythia. And we've already seen the efficiency of Pythia in the previous part of the lecture. So this is, again, the interesting picture, more interesting picture, perhaps. This is what you get as you vary the main memory bandwidth for single core workloads averaged. And this is what you get on average. It seems like Pythia actually loses performance in this case. These are different workloads. New workloads, okay. So you can see that as you add new workloads, things change. But you've seen this earlier with, for example, memory scheduling mechanisms also. Memory scheduling mechanisms are also quite workload dependent. I don't like this baseline over here. There's an E. Anyway, we'll correct it later. But basically, you can see that at lower, because Hermes is very frugal, and also it doesn't generate a lot of requests. At lower bandwidth levels, it outperforms PTA. At higher bandwidth levels, PTA becomes higher performing because it actually exploits that bandwidth that's available. Whereas Hermes doesn't necessarily exploit that bandwidth, right? Because it's much more frugal. And we just discussed that. And if you combine them, it's actually at especially higher bandwidth configurations, you get a lot higher benefit. Okay. Okay, let's take a look at another example. So as I said, Hermes is really complementary to any prefetcher, right? You can have any kind of prefetcher or any type of prefetcher, many prefetchers in your system, and you can still predict whether your load will go off chip, and then employ Hermes with the prefetcher. Although there could be interesting interactions to explore as you add more and more prefetchers, probably, because they could be generating a lot of requests internally as well. And Hermes improves performance over all of them. These are some state-of-the-art prefetchers that we're not going to cover, but some of these are offset-based prefetchers, for example. Some of these are more spatial prefetchers. I think in backup slides I have some links to some of them, but the paper clearly has them. You can see that PTA is the best performing among all of them. Okay. Okay. So the overhead of Hermes, as you expected, is much lower than PTA. It's much smaller because of the learning it employs. Okay, I think I've said a lot of these, so I'll let you with that. So this is a slide. It's a single slide summary. And this is open source. You can build on it. In fact, your whole open source, a lot of stuff. Are people building on it? I think they have. That's good. In Hermes. Okay. Okay, maybe you're going to talk about them in a later lecture. State-of-the-art research lecture. That's the good thing about open sourcing. Basically, you enable your work to have higher impact and also enable other research that may not have happened. I think that's really important to do. Okay, and that's the Hermes paper. Before, yes. Yeah. Mm. Yes. Yes. So basically, what you're saying is predict whether data will not be reused and have some other paths to bypass some parts of the caching hierarchy. Yeah. Yes, certainly. I mean, some of those paths actually exist already to bypass the caches. Maybe not everything, not every combination exists, but there are some cases where you can bypass some of the caches today. Yes. Yes. So, for example, when you get the data from memory for a critical load that you're waiting, that is stalling the window, which is reorder buffer, there is a path to supply that data directly to the, essentially almost close to the functional unit. Not exactly the functional unit, but the misstatus holding registers of the L1 cache. So you can actually supply it directly to the L1 cache. That path exists. But the reverse path usually doesn't exist because there's people have realized that once you get the data, supplying it immediately without going through the cache hierarchy is probably a very good idea because you know that you need that data at the load store unit, right? The other path has not been built because there was no real need to build it so far. Yeah. Any other questions? Okay, before I take a break, I will say that there's more work on data-driven prefetchers. These are actually more software-based works. For example, this work formulates prefetching as a next token prediction and propose a long short-term memory-based prefetcher. Very interesting. Quite expensive to build in hardware, I think. But I believe this employed in some software prefetching techniques. As I said, prefetching is a very general idea, right? It can be employed at the system level. If you're, for example, running a program in a data center, and if you need data from remote memory, you don't want to wait for that data to come back. You can predict the access patterns. And I think the context in which this sort of prefetching is employed is more at that software level context. This is a work from Google. Another work, I guess similar people who worked on this is these folks use graph neural networks, and they basically learn the control and data flow dependencies in static codes using graph neural networks to use for branch prediction and prefetching. And these were published in machine learning conference, as you can see over here. Why didn't you publish at a machine learning conference? Sorry, I had to say that, because if you publish at a machine learning conference, everybody cites your paper because nobody reads other papers, right? Other papers are useless. I'm joking, of course, right? That this is one of the interesting things that happen in today's world. I'm just joking. Do the right thing. Okay. And there's also more work that looks at, for example, multi-layer perceptrons to predict the next cache line offset. And this is a work that builds on Rahul's paper, not Hermes, PTR, right? Which significantly reduces PTR storage overhead. And it uses another type of reinforcement learning called multi-armed bandit type, which has its advantages and disadvantages, I think. But you can read the paper for more detail. Okay, I think this is a good place to take a break because I'm pretty sure we have, yes. So let's come back at 14:35, 15-minute break, and then we will continue prefetching. Okay, I think it's time to get started. Everything is okay online? Yeah, okay. Okay, so we've covered some more sophisticated prefetchers, machine learning based prefetchers, as you have seen. As I said, there's a lot more possibility in this area for sure. And there's a lot more creative work to be done. So that's the nice thing about this area. I will also very quickly go over some specialized prefetching mechanism for targeted workloads or more hardware software co-design. We briefly discussed this, but some workloads are really important, graph analytics, for example. And prefetching for these may be very difficult with general purpose mechanisms. Because as you can see over here, you have a bunch of lists and you got to traverse through these lists based on pointers. So you have pointer chasing, yes, but the pointers that you chase very much depend on where you are in the graph, essentially. Which means that if you know your data structure and if you know the semantics of what your application is trying to do, and if you communicate that information to the underlying hardware, perhaps you can do a much better job than being general purpose, right? Because if you're general purpose, for example, with a Markov prefetcher, it's very difficult to do these things, right? Okay, I will not go through this in detail, but there's still there's work in this area that talks about graph prefetching. These are some example papers. For example, communicating memory access patterns from the higher level data structure level to the hardware can actually provide much better benefits than general purpose prefetchers or even somewhat specialized pointer chasing based prefetchers. And this other work looks at a programmable prefetcher that gets triggered based on user-defined application events, which is actually interesting also. That's not a new idea in that sense. There have been ideas where if something happens, you actually trigger some code that executes in the processor. But in this case, they're specializing to the graph analytics prefetching. It's interesting. We have done some work where we can communicate information about the higher level program semantics to the lower levels of the hardware. We've discussed this actually briefly in maybe lecture 1 or 2. We talked about this XMEM, and we talked about the communication bottleneck between software and hardware, where hardware doesn't have enough information about what's going on in software. And in this work, we have a way of communicating information about memory regions, any kind of characteristic. It could be a locality characteristic, compressibility characteristics, prefetchability characteristic, access pattern characteristic, etc. We have a general purpose way of communicating that information to the underlying hardware. And this Metasys work has an FPGA-based implementation of this expressive memory work. And some of the use cases of this expressive memory and Metasys is really prefetching data based on information you have about memory regions that's communicated to the hardware. For example, different memory regions may have different access patterns, and they can communicate that information. And you can read one of the use cases over here, but there could be other use cases of this sort of higher level interface that enables communication between hardware and the software. Okay. There's also work on prefetching for functional languages and different types of workloads that I'm not going to go into, but these are interesting also, although maybe a bit too specialized. Any questions? Okay. If no questions, now we're going to cover a bigger area of prefetching, which is actually very general purpose, more general purpose than anything we have seen, in my opinion, which is execution-based prefetching. This can cover any access pattern, essentially, although you will run into some trade-offs, as you will see. So the basic idea is very simple. You prune part of your program, create a thread, and pre-execute that thread. It sounds nice, right? The sole purpose of pre-executing that piece of the program is to prefetch data. Now, of course, now I've said this, you could say, okay, you could use this program for something else. Yes, of course. You could use this program for predicting branch directions, as we will later see very briefly. You could use this program for verifying results, potentially, if there are errors that happen. You can compare the results, and this could give you a potential indication of whether you've done something wrong. So the idea of execution-based or pre-execution or post-execution using a pruned part of the program is much more general than prefetching, actually. Prefetching is one application of executing or redundantly executing a piece of the program. In this case, with the prefetching application, you only need to find pieces that lead to cache misses. So because you really want to be frugal, because executing a thread is expensive, of course, depending on how you do it, it's more or less expensive. But if you find code pieces that lead to cache misses and execute only those code pieces and specialize that code piece to generate addresses, you can be much more efficient, as we will see. So we will call this pre-executed program piece a speculative thread, because this could really be considered a thread. In fact, in some cases, it is really a thread. Maybe it's a lightweight thread. It may be hidden from the operating system, for example, but it's still a thread. It's a hardware thread, some sort of hardware thread. This hardware thread can be executed, or it could be a software thread also, actually. I should just call it a speculative thread. It could be executed on a separate processor or core. It could be executed on a separate hardware thread context within the same core. For example, think fine-grained multi-threading or simultaneous multi-threading. It could be executed on the same thread context that the main program is executing on in idle cycles, basically during cache misses. And we're going to see a specific example of that. So there are multiple issues over here. One is how to construct the speculative thread. I kind of hinted at this, but software can construct it, hardware can construct it, or it could be done in a coordinated way again. For example, software, you prune the program. Programmer can prune the program. Compiler can prune the program and say, oh, these are, for this load instruction, I think this, if you pre-execute this code, you will prefetch it, prefetch the data nicely. Now the question is, where do you put the spawn or fork instruction for before you get to that load instruction? Right? So you could do this purely in software. You could do this purely in hardware. Clearly, there are trade-offs over here. You could use the original program, actually, without constructing anything, without any specialized thread construction, but you execute the original program faster without stalling and without abiding by correctness constraints. Essentially, you execute this original program much faster than you would, but maybe not fully correctly. Your goal is to just generate prefetching requests, which is a nice idea, I think, as we will see, but it may be a little bit expensive in the sense that you're executing a lot of instructions that you may not necessarily need to execute to generate prefetches, right? Pruning is nice because you really try to slice part of the program that leads to the cache miss. And it could be very efficient, but it requires a mechanism for pruning. Whereas executing the original program doesn't require any mechanism for pruning. You can execute the original program. And maybe over time you prune it. So these ideas are not necessarily completely orthogonal to each other. So this speculative thread, the key goal is really if you use it for prefetching, the key goal is to discover misses, initiate them, and hopefully complete them before the main program gets to the load, and so that the main program doesn't incur the cache miss. Right? You can avoid waiting or stalling, and you can compute less in the speculative thread. Right? So goal is to get ahead of the main thread somehow. Right? So to be able to do that, the speculative thread performs only address generation computation, maybe branch prediction if the branch predictor cannot predict the branch, for example. Or maybe in some cases, you don't even need to do branch prediction in this thread because you are within a loop and you're actually unrolling the loop, and the branches are going to be, at least the loop branch is not going to be useful for you to predict. You may need to predict some values so that you can actually construct this thread. There might be some unknown value that leads to a branch that determines which path you're going to take, for example. You may need to do some prediction so that you can prune the program. So basically, the goal is to construct a small slice that would do the address computation for a load instruction by getting rid of as much as possible from the original program. That's the idea. And there could be many techniques you can employ, including speculative technique, because this thread is going to be purely speculative. Right? It's not going to generate any exceptions. In many cases, it's not going to be even visible to the operating system. You're going to hide this, basically. It's going to execute. While your program is executing, you will fork this thread. That thread will execute somewhere else and generate prefetches for the main program. That sounds good, right? So you can play a lot of tricks with this thread. And we will see some tricks in particular case. as I already said this basically, it's purely speculative. There's no need for recovery of the main program or the speculative thread if the speculative thread is incorrect. Okay, so this is an example. I like this example because this example comes from this ISCA paper from Zilis and Sohi. And the idea is basically, the general idea is thread-based pre-execution. This is the main program that you're executing, that you're supposed to execute accurately. And you identify that this load is actually missing in the cache a lot. So you construct a speculative thread. We will see some example of the speculative thread soon. You determine a fork point. When the main program gets to that fork point, a fork point needs to be much earlier than the load, of course, so that you can hide the latency of the cache miss. When the main program gets to that fork point, it forks this thread. This thread gets executed in some other core, in some other context, for example. In this case, it's executing concurrently with the main program somewhere. It gets to this cache miss, gets to this load, generates this cache miss, and the cache miss is handled long before the main thread reaches the load. That's the idea, right? It's a nice picture. You could do the same thing for other, let's say, performance degrading instructions like branches. Right? If you have a branch that's highly mispredicted and you don't know how to design a predictor that can predict this branch easily, what you could do is you could do pre-computation-based prediction, again, thread-based pre-execution for that particular branch's prediction. You fork the thread long before you come to the branch, and then this branch, you essentially execute a piece of code that would compute the branch condition and the direction and the target, and then you buffer that prediction somewhere, and when the branch is fetched, you use that prediction immediately, and you disregard whatever your other predictors are telling you in the hardware. Sounds like a beautiful idea. Yes? Mm-hmm. That's right, yes. So this thread actually is doing that address computation. That's right. Not necessarily binary. It could be the program. You could compile a different thread. But yes, if it's done in hardware, you need to really examine the binary, yes. You select instructions that would actually lead to the computation of the address of the load much earlier. And you could imagine many cases, like, for example, this load, before this load, you may have a huge loop that does something, right? Adds to a race. But you know that you're going to get to this load at some point. It's control independent of that loop. And you put a fork before that loop. So there could be a huge loop over here that has nothing to do with the load. But you could raise the address computation over here. Make sense? So there's parallelism that you're exploiting and independence and you're exploiting in the instruction stream. Same thing for cache misses over here. Now, not cache misses, sorry, branch predictions. But branch prediction requires some explicit communication between the thread and the branch or some sort of new addition. Whereas load doesn't require any explicit communication because if you fetch the data into the load, this load computes its address and finds it in the cache. Right? Whereas branch prediction, you need something else to communicate from the speculative thread to the branch prediction hardware. Okay, so these papers are actually some early papers on this topic. There's a nice technical report on this topic, simultaneous subordinate microthreading, which is a mouthful. It's known as helper threading, basically, in general. I like assisted execution also. You're really assisting the main program. But this is a nice idea that has been explored a lot. But there are a lot of issues over here. So one is assuming you constructed the pre-computation thread or pre-execution thread, where do you execute it? When do you start it? When do you terminate it? These are all interesting issues. As we have said, if you put it in a separate core, you have least contention with the main thread because the multiple threads are executing now. But you may not share the caches at the lowest level, meaning L1 level in a different core, right? So when you prefetch into the L2, but maybe not the L1 of the other core, right? You can execute on a separate thread context on the same core. You may be doing simultaneous multi-threading or fine-grained multi-threading, interleaving the threads. This leads to more contention. While the main thread is executing, the helper thread is also executing, meaning that main thread can be delayed because of that contention. But you may still get benefit because there's still idleness, fine-grained idleness in the cores. You could also do it in the same core, same context, which is the, let's say, most aggressive version and perhaps least intensive version in terms of hardware. You don't need a separate context, because whenever you execute a helper thread in some other thread context, hardware thread context in some other core, it's always good to say that, think that, oh, what are you not executing on that context, right? Maybe you're reducing your thread count by 1, assuming your program is multi-threaded. If your program is not multi-threaded and you have 100 cores, then it's good. You can use all of those cores for that single thread, right? Maybe your energy efficiency is not that good, but you can improve performance. So this third option is actually very frugal in the sense that it uses the same core, same context that the program is executing on. But when main thread gets stalled, it really executes this thread, speculative thread, that will do prefetching for the rest of the program. We will see an example of this. So the next question is, when do you start the pre-computation thread? Meaning, when do you fork it? You need to insert these spawn or fork instructions well before the problem load. Some people have called these problem loads delinquent loads. I like problem better, maybe. Delinquent makes it a little bit, I don't know, intense. Yeah. So the question is, of course, how far ahead? This is very similar to essentially inserting a prefetch instruction, right? A prefetch instruction is a single instruction. Right now, we're not inserting a prefetch instruction. We're just inserting a fork instruction that will create, that will spawn, that will essentially fork another thread to be executed. It's a very similar problem, but you need to now take into account the execution of many instructions as opposed to a single prefetch. So if you do too early, prefetch may not be needed. If you do too late, prefetch may not be timely. So you're at the same juggling that you need to do. It's much harder to do this in software, again. Although here with software, you still, because you're pre-computing, as opposed to trying to insert a single prefetch instruction based on some regular access pattern, you're much more general. So in this sense, I'm a little bit less pessimistic about software over here, because you're really executing a thread and software can construct that thread very nicely. Whereas it's much more difficult for the software to identify the access pattern of an exact prefetch instruction, right? As we have discussed in the last lecture. That's a much harder problem than software constructing, oh, I have the slice. This is the address computation that will lead to this load. The software can do that much more easily and hopefully get the address prediction correctly, right? So I think in this case, software has an advantage over hardware. Although hardware-based construction can also be possible, hardware may not have the scope of the software. For example, software can analyze the code and say, okay, I have this huge loop here, and then I have this load that usually misses based on my profiling information. I'm going to ignore this huge loop and generate the address for that load that misses. And then I'm going to put the prefetch instruction, not prefetching instruction, fork instruction before the loop. So software has a much more flexibility over here without necessarily having a predictable address pattern. Right? You compute the address pattern. As I said, you can also start the pre-computation thread when the main thread is stalled. And we will see an example of this also. And then there's a question of, when do you terminate the pre-computation thread? You can, for example, okay, clearly, when the pre-computation thread ends is one way of terminating it because it stops. There's no more code to execute. That's one way. But if the pre-computation thread is too late, for example, or for some reason it's executing for too long, you may actually have some cancel instructions. We're going to see an example of this. Or you may actually have some effectiveness or contention feedback. So you can actually throttle the pre-computation thread also. All of the ideas of prefetcher throttling can be applied to thread throttling in this particular case, to throttle, let's say, maybe inaccurate or maybe not so good pre-computation thread. There may be inaccuracies in the pre-computation thread because you may have played tricks like predicting branches, predicting values, getting rid of some instructions aggressively, and they may actually make your pre-computation thread not so accurate, right? Depending on the access pattern, etc. Okay, yes?
On the where part,
Mm-hmm.
the first point is separate.
Mm-hmm.
Put on the separate. The data is going to come to shared.
Exactly, yes. Mm-hmm.
You need to account for that.
Yeah, exactly. Mm-hmm. Yeah, the data access latency is really the access latency of the shared cache. If you're not sharing anything across those cores, then you have a problem. But usually you're sharing L2 or L3 caches. That's right. Yes. Yes. Okay. So there's a very nice paper that talks about some of the software controlled pre-execution issues in SMT, simultaneous multi-threading processors. I'd recommend this. This will be part of your homework also as a potential paper to read. It discusses many issues that I kind of talked about related to software-based pre-execution. I like some of these figures over here. And it basically motivates using pre-execution in different types of applications. For example, you may actually be doing multiple pointer chains. If you're doing many hash table lookups, for example, you can think of these as different buckets. And whenever you access one bucket, you go through a linked list. While you're doing that in the main thread, you may actually be speculating and accessing other buckets, right? So it may actually create pre-execution threads that access other buckets in the hash table. And this works, this nicely parallelizes things, right? You could also, of course, consider doing this in regular parallelization. It's good to think about the differences between this and regular parallelization. Regular parallelization requires you to be correct completely. This is completely speculative. Right? Well, of course, there's other array accesses where you can actually do this also. Like while you're accessing this array, you may be accessing another array or the same array in a different way using different functions. There are multiple procedure calls while you're actually executing, while the main program is executing this function. Speculatively, you may actually launch other functions, as you can see, and also a control flow paths. While the main processor is executing this basic block, if you will, you may actually launch other basic blocks to pre-execute, right? That way, you can actually cover different paths potentially. I'm not suggesting this is the best solution, but you could actually do a lot of things if you know the software structure. Actually, a lot of the graph processing works that came later on are really building on this type of work, in my opinion. They're trying to understand the access patterns and try to construct threads or try to guide the prefetcher, make it more programmable so that it can actually prefetch some things before the main program gets to it. Okay, so this is an example. This is a heavy code over here, but what I want to point out over here is this is a famous workload in spec benchmarks, MCF. It does vehicle scheduling. It's a single-threaded workload. But basically, it traverses a bunch of lists. It traverses a trips list over here. And then within a trip, it tries to schedule some things over here. I'm not going through the semantics of it in detail, but essentially, you can see there's a for loop that looks at different trips. And then it has a while loop. Within a trip, it looks at how to schedule that trip, for example. Now, if you read this thing, what this thing says is, if you want to actually do pre-execution somewhat minimally, you can modify this code such that you invoke a pre-execution starting at the end of 4, like let's M4 over here. So basically, you insert a fork over here, pre-execute start, N4. N4 is basically the program counter you should start at, which means that while the main when the main program gets to this pre-execute start, it will launch a pre-execution thread starting from N4. Okay, so it will. What this does is the speculative thread will essentially go to the next iteration of the for loop. So it will do the next while loop, right? So you're really parallelizing the while loops across the while loops. You're really parallelizing across different iterations. You're really prefetching the next iteration's data while you're doing the main iteration. That sounds good, right? You could also try to parallelize this program this way. You could do it actually, but now you got to be perfectly correct. In this case, you don't need to be perfectly correct. And these are the ISA extensions. So you need some pre-execution start. You can read this on your own, but essentially what this does is it has a start PC, which was the end for location over here, which is essentially the end of this iteration of the for loop. But you need to, of course, account for the next iteration to begin. Essentially, it requests an idle context to start pre-execution at the start PC, and maybe optionally stop when max instructions have been executed. And thread ID holds either the identity of the pre-execution thread or -1 if there's no idle context. So this may not succeed, basically. That's the speculative part. If you're doing pure parallelization, this is one way of doing parallelization, but you need to wait until you can actually do the parallelization, perhaps. Right? Okay, this instruction has effect only if it's executed by the main thread. That's another option, basically. Do speculative threads spawn other speculative threads? In this particular case, the person who wrote this paper decided that's not a good idea. So basically, it doesn't have effect if a speculative thread executes a pre-execute start. A pre-execute stop, the thread that executes this instruction will be self-terminated if it's a pre-execution thread, no effect otherwise. Pre-execute cancel, thread ID, terminate the pre-execution thread with thread ID. Again, this instruction has effect only if it's executed by the main thread. So there could be some reasons to cancel. I don't think it's used in this particular code, but again, you may want to cancel it if for some reason, right? If you're actually out of the code that you don't want to you want to prefetch, for example. Okay, and they evaluate this sort of pre-execution that is applied to different programs. These are some Spec 2000 programs at the time, and they see significant benefit. So in some cases, for example, they lose performance as execution time on an SMT processor. In this case, for example, they lose performance, but in many cases, they gain a lot of performance. And so in this case, for example, on multiple spanning tree, I think, MST. That's not Spec 2000. Okay, there might be other workloads over here, clearly. They gain about 36% performance improvement. So you can see that this could be quite effective, as you can see. Okay, and this is, I think, if I remember correctly, this is not doing extremely specific pruning of the code. Now, if you do pruning, which we will talk about, which some other works do, and these are some nice papers that talk about pruning. I actually like both of these papers because they try to understand these difficult to predict instructions, both in terms of branches and misses, cache misses, and they try to understand how. Essentially, they call it backward slice of that instruction. You basically look at which instructions feed into this instruction, and that's the backward data flow slice that go into this instruction. And ideally, you would like to identify this backward data flow slice that lead to the address computation or the branch target determination. And those are the only instructions that you really need to execute to get the correct, hopefully correct, prediction and correct address. And this is one example from another spec workload, VPR. Does anybody know what VPR is? It's actually used in processor design. Virtual place and route. It does placement and routing. Not with reinforcement learning. It uses classical techniques for placement and routing. But that was a benchmark that's used in spec. It's a single-threaded workload. And it does something. So you can see over here that these folks have identified that this particular load instruction usually leads to cache misses. And this particular branch instruction that compares this cost to this cost usually is mispredicted. So you have the nightmare of a processor designer over here together. The same line of code leads to a cache miss, and the branch is dependent on that cache miss, and the branch is usually mispredicted. Okay. So if you actually do get both of them right, you boost performance significantly. Okay, so how do you do that? Basically, these folks identify this instruction, and they basically decide a fork point. What am I looking at over here? This was the add to heap function where we encounter this thing. So this function is called from an outer function, which is node to heap. And they basically say, we want to add a fork point somewhere over here, beginning of the node to heap function. And that's going to be our fork point based on what they have constructed, which we will see also. So basically, you have a fork point before the function is called. And within the function, you see that there's some code to get to it. Okay. And this is, again, this is not meant to cover everything over here, but this is the assembly code for that add to heap function. And the problem instructions are in bold, they say. Bold, don't get bold. It's not this highlighting, it's this bold. So this instruction, LDS, for example, and this FBEQ, those are the problem instructions. And the shaded instructions comprise the unoptimized slice. But if you, for example, look at an unoptimized slice, it's actually pretty big. And then they basically go and identify what they can optimize such that they would compute only the load instruction address and the branch instruction target. And they come up with the slides, basically. You can see that if you actually go and hand optimize the code. I think in this case, they actually hand optimize the code. They didn't use a compiler. This is the slice that you want to execute. Much better than this mess. So clearly, it's not 20 plus instructions. It's really only 1, 2, 3, 4, 5, 6, 7, 8 instructions. And there's a loop inside there, as you can see. So this is their pre-execution thread, essentially. And this is the kind of optimization that you can do. And I'm not even sure if they did any speculative optimizations here. I'm not sure if they did any. I don't remember, actually. I don't think they did. They may have predicted one of the values. I don't know. But yeah, they have a live in, actually. So maybe they didn't predict the values. OK. Does that make sense? So this is the idea of constructing a thread to pre-execute some code to prefetch, or in this case, both to prefetch and also to compute the branch. Make sense? And this works, actually. People have done it in real systems, and they've seen performance benefits. Although there are downsides, as we have discussed. In some cases, you lose performance, as we have discussed, because there's contention, and the benefit may not be as high to overcome the downsides of misprediction or the contention, right? Because when you execute the thread that's speculative, you're really contending with the main thread. OK, let me give you some idea that's very close to my heart. This is my own PhD thesis. Basically, I've given you the basic idea earlier, but I want to go through it because this is the right place to go through it. Basically, what we have done is also an execution-based prefetcher. Another way to look at it is Runahead execution is a technique to obtain the memory level parallelism benefits of a large instruction window. I will not go through this in detail. I have some backup slides, but essentially the idea is very simple. When the oldest instruction is a long latency cache miss, the processor checkpoints the architectural state and enters a speculative processing mode where it speculatively executes the instructions in the main thread, but in a very speculative mode. We're going to see what that speculative mode is. The speculative mode is called Runahead mode. In this mode, the goal is to speculatively pre-execute instructions with minimal stalling. The purpose is to generate prefetches, essentially. Very similar to the purpose of that pre-execution thread, except we're not going to go through any of the pain of constructing that speculative thread either by hand or compiler or by software. The hardware is going to construct that thread. It's not going to construct that thread. It's going to use the main program. It can later prune that thread, as we will see in later works. The long latency instructions and any other instruction that you think you don't want to execute is marked in a special way, invalid, and dropped, essentially, so that they don't occupy resources in the processor. This enables room for later instructions in the window to come into the processor. So the first long latency instruction is also marked invalid and dropped because you will not get the result for it. It's going to take a long time. So it's going to get out of the processor so that you can make room for getting new instructions into the processor. When the original cache miss returns, the processor restores the checkpoint, it flushes the pipeline, and it resumes normal execution as if nothing has happened. And nothing really happened architecturally. Architecturally, you're really starting as if nothing happened, re-executing the original instruction and everything else. But hopefully, microarchitecturally, you've done a lot, meaning prefetched a lot of things into your caches. So that's the idea. So I gave you this example at some point before. Ideally, we want perfect caches, so you never stall, at least for loads. But what we get today is small windows. So when you get a long latency cache miss, after some point, that becomes the oldest instruction in the window, and then you cannot bring new instruction into window. So your window stalls, and then that miss completes at some point, and then you can continue filling instruction into your pipeline and window. After some point, you get to another long latency cache miss, and then you stall again after some point. And this is very common. We have seen that in earlier lectures. Most of the time, processor stalls for data-intensive workloads. The idea in Runahead is to avoid the stalling and convert the stalling into pre-execution, essentially. When the long latency load miss becomes the oldest instruction, you checkpoint the architectural state. We wait until it becomes the oldest instruction because it gives you a clean place to checkpoint the architectural state. If you didn't wait, you're kind of messy because the oldest instruction is not, there are other instructions before you, and you don't have a very clean state. You could do it, but it becomes more expensive. And then you enter the speculative processing mode where you keep executing instructions and dropping instructions that are taking too long, dropping instructions that may not lead to address computation, for example. And hopefully, you will get to the second load, and hopefully you'll be able to generate the address for it and start the miss for it. And at some point, the miss that caused entry into Runahead mode returns. We flush the pipeline, restore the checkpoint. So it takes some time, actually. There's some red over here still because there's some flushing of the pipeline. And we execute as if nothing happened. We execute the load, and the load hits in the cache. And when you hopefully reach the second load, when you're doing the main thread execution, it hits in the cache. So you don't observe the second stall because you used the otherwise stall cycles for pre-executing the main program and prefetching and parallelizing the misses. That's the idea. Okay, so I think I've said a lot of these things. The processor speculatively pre-executes the program without stalling for long latency instructions. Pre-executed loads and stores independent of the L2 miss instructions generate very accurate prefetches, data prefetches. And again, this is really, you're really using the program that will compute the same way. You're not trying to predict anything, right? You're just, the only prediction you're doing is the program will execute the same way, right? Instructions on the predicted program path are prefetched into the instruction cache and outer cache levels. We didn't talk about instruction prefetching that much. We'll talk about it hopefully if time permits. But this is a method, a general method for prefetching for both data and instructions. And other things also. If you have a prefetcher in the system, now you're really training it with future information. You're really training your branch predictor tables with future information. So you're really priming them, which is really interesting also. So there could be other things over here that could be interesting. In fact, doing this sort of processing, speculative processing of later part of the program can give you information about what will happen into the future. And this future information can be useful for managing other parts of your system like caches, etc., which we clearly have not done in this work. But the basic idea is you're really executing into the future mostly accurately, as we will see. Most of the time, you're on the correct path as if the program would execute. So you're really uncovering information about what would happen in the future. So you could go back and use that information for replacement policy, insertion policy, etc., that we did not do in this work. Okay, let's go into this a little bit more. I'm going to talk about instruction processing. I'm not going to talk about checkpointing, etc. These are techniques that you can use. Instruction processing is interesting, but because it's essentially the same as normal mode instruction processing, except it is purely speculative. We don't update the software visible state. From the software's perspective, the Runahead execution doesn't happen. No architectural register or memory state is updated, essentially. And L2 miss-dependent instructions are identified and treated specially. They're quickly removed from the instruction window. Their results are not trusted. Another way of dealing with them could be predicting the values of those L2 miss instructions. And we have actually analysis of that in my thesis. You can take a look. Even predicting a value of 0 is actually not bad. Okay, so let's take a look at how these L2 miss-dependent instructions are treated. There are two types of results that are produced, invalid or valid. Invalid means it's dependent on L2 miss, but more generally, invalid means that I could not and I don't want the result of this instruction. I want to get rid of it from the processor immediately so that I can get to something that hopefully is going to be useful for prefetching. Right? That's the idea over here. So you could essentially mark anything you want invalid. Right? For example, in later works, we marked some floating point operations invalid because we don't want to execute them. Probably, it's very likely that you're not going to use floating point computation to calculate an address. A floating point computation may lead to a branch that you predict that would lead to an address that may miss, but the likelihood of that is relatively low. So it's good to get rid of floating point instructions as invalid. Because we're not constructing a special thread, the way we get rid of these instructions is while we see them, marking them invalid. Right? If you were constructing a special thread, you would get rid of some of those floating point instructions. Okay, so these invalid results are marked using special bits in the register file and the store buffer. So these need to be added to the processor. And they're not used for prefetching or branch resolution. So you don't trust these values, basically. So you trust the branch predictor more than a branch that actually consumes an invalid value. You could predict the invalid value, of course, right? That's another different thing. Then who do you trust? Do you trust the value that you predicted, or do you trust your branch predictor better? So there needs to be confidence levels over there also. Okay, so how do you remove the instructions from window? Again, this is not a difficult process. We use exactly what the processor does today. Essentially, when the instruction becomes oldest, an instruction becomes oldest, it's examined for, I call it pseudo-retirement, because you're not really updating the architectural state. If it's an invalid instruction, you immediately remove it from the window. So invalid instructions occupy resources until they become the oldest instruction in the window. But the hope is that no instruction stays long in the window, because long latency instructions are quickly marked invalid. Right? That's the goal over here. So this could be combined with Hermes, for example. When you predict that some instruction is going to be off chip, you don't need to wait until you verify that prediction. In Runahead mode, you basically use Hermes and you say, okay, I'm going to start the request, long latency request earlier. And that could actually accelerate Runahead execution and could amplify the benefits of both. Right? I've given you some ideas. Yeah. If it's a valid instruction, then you remove it when it completes execution or when it becomes invalid. Right? And these instructions free their allocated resources so that something else can come into the window. Right? And this processing in Runahead mode is actually very fast, as I said. You could make it even faster by dropping things. One of the hairy things in Runahead mode is store-load communication, because you don't want to update memory, right? Because this is purely speculative. Then the question is, what happens if you do a store to a memory location? This exists in all pre-execution-based mechanisms. I kind of didn't talk about that earlier. But if you're generating a pre-execution thread, what do you do with stores, right? Because this is supposed to be purely speculative. Where do you write it? There are multiple solutions to this. Sometimes you create some speculative locations and write them over there. Sometimes you ignore the stores. That also happens. In our work, we identified that this is important because we were doing this work initially for x86. And x86 actually has a small number of registers compared to many other ISAs. And as a result, you have a lot of communication between stores and loads, especially through the stack around the function calls, or if you're spelling the registers, for example. So one solution could be, and this is the solution that we employed, when you finish a store, you write the data and its status, invalid status, to a dedicated memory called Runahead cache. Bad naming, should have been named something else, but it's really structured as a cache to be fast. And the sole purpose of this cache is to do data communication through memory in Runahead mode, through stores and loads. So a dependent load reads its data from the Runahead cache or other structures also. If it cannot find it, for example, in the store buffer or the Runahead cache, then it reads the data cache. Okay. And this doesn't need to be always correct, essentially. The size of Runahead cache can be very small because the whole mode is speculative. You could completely eliminate this, but we found out that this is needed because this is important in x86 architectures, at least. Okay. So branch handling is one other place where things get hairy, but again, we take simple decisions. If you have a branch that's invalid, meaning it's sourcing a data that's dependent on L2 miss, or it's sourcing the data of an instruction that you decided to be invalid, you cannot resolve it. Essentially, this is not a problem if the branch was predicted correctly. Branch could be predicted correctly based on its real data value or real data value that it should have used. It's a problem if it's mispredicted. Now you have a mispredicted branch that you cannot resolve, and the processor stays on the wrong program path until the end of Runahead execution. Okay, this is not necessarily bad, because wrong program path actually can lead to still good prefetches for the correct program path, but it's better to be on the correct program path in general, according to our analysis. We analyzed wrong program path and versus correct program path a lot, and our conclusion is this basically: it's better to be on average on the wrong program path than not being on any path. Meaning, if you're on the wrong program path, you're prefetching data for the correct path for performance. But it's better to be on the correct program path than to be on the wrong program path for even prefetching data. Does that make sense? So essentially, stalling magically on a mispredicted invalid branch is worse than keeping on executing for performance. For energy, that may be a different equation. Okay, if you have a valid branch, that's great. In the Runahead mode, you keep resolving them just like you would in regular execution. So basically, the takeaway, I think, is that you do the same thing that you would do in normal processing, except you're doing it speculatively and with some changes to this invalid structures. And these are the structures that we have changed. So it's not a lot, actually, although it touches a lot of parts of the processor. So you need to checkpoint the register file, at least the register alias table. And there's some hardware cost over here. And then you need to have some specialized control mechanisms. So I'll go through the advanced and disadvanced while I talk about some results. So it turns out this is actually very accurate. Our results show that this is more than 95% accurate actually for data and instructions because it follows the program path to all cache levels. That's also another thing. You don't need to think about cache levels, right? I just prefetch into all of the caches because I'm going to use this data in the future. It's simple to implement. Most of the hardware is already built in. There's no waste of hardware context. It uses the main thread context for prefetching. But again, you don't have to do that. For example, IBM Power 6 used some other thread context because they didn't want to use the same thread context. They said, oh, we have already thread context available. Let's launch the Runahead execution on the other thread context. There's no need to construct a special purpose pre-execution thread for prefetching, which I think is nice. So disadvantages and limitations, some of these are common with other pre-execution approaches. Clearly, all of these pre-execution approaches, including Runahead, lead to extra executed instructions. So there's some energy waste. If you're not getting any benefits, you're really purely wasting energy. And this is a real problem on some workloads. For example, in workloads where you're doing heavy pointer chasing, pre-execution may not actually buy you much because the address that you're going to hopefully generate is dependent on the address that you just missed on. So your cache misses are dependent on each other, basically. So you will purely be executing extra instructions without getting benefit. And that's bad, clearly. So we have mechanisms to fix that. And those are later work that I'm not going to talk about. You're limited by branch prediction accuracy. That's actually true for a lot of pre-execution threads. But here, actually, you may be more limited because we're really following the main program path. If you have a specialized pre-execution thread that you construct, some of the branches you could get rid of. And you don't need to even predict them, right? That's one disadvantage of Runahead execution using the main program for prefetching compared to creating a specialized thread. Here, we don't get rid of branches. At least there could be other mechanisms to get rid of branches, of course, that you could add. It cannot prefetch dependent cache misses. I already said this. If a cache miss depends on a previous cache miss, then you have a problem. Again, there are solutions to this, at least partial solutions to this. And the effectiveness you get here is available by memory level parallelism, meaning while you're waiting for a cache miss, you hope that another cache miss can be uncoverable and startable instead of waiting, right? Well, with this sort of execution. If you don't get to another cache miss, then you have a problem. And you're limited in terms of how many instructions you can execute because you're going to go back to main thread execution when this thread ends. Or when the original cache miss that caused entry into Runahead mode returns. So the number of cycles you spend in Runahead is limited. If you're using the same hardware context. If you're using another hardware context, now you could be doing Runahead on that context. I don't want to call it forever, but technically forever, right? Or you could be doing Runahead for a long time, and then you could be restarting the Runahead, etc. So there's a lot of interesting ideas over here, right? Okay. So prefetch distance, how far ahead to prefetch is limited by the memory latency. I just said this. How long you stay in Runahead mode is dictated by, at least in this implementation of Runahead, by how long you stall for the cache miss. So let me give you some performance results. These are results from workloads that Intel used to use to design its processors at the time. And we see that, so this is the only prefetcher that's used here is a locality-based prefetcher, like we discussed yesterday. It's an optimized version of that. And you can see that on average, that prefetcher is pretty good. The blue bar is really the real baseline. Compared to the blue bar, adding Runahead provides you about 22% performance, which is not bad. Only Runahead by itself actually is better than the prefetcher, but not in all workloads. In some workloads here, you have better, highly predictable memory access patterns, and prefetcher is actually better. So it's good to look at this. And there's a wide variety of workloads over here. Okay. So compared to building a large instruction window, Runahead is actually a cheaper way of getting the benefits of a large instruction window. It's really running ahead and capturing some of the benefits. It's as if you had a large instruction window, right? That is dependent on the latency of the cache miss. Because you're executing ahead, right? Without building that window. You're using the exact same window. So our baseline was 128 entry window, 128 instructions maximum from the oldest instruction. And if you add Runahead on top of that, you gain this much. Instead, if you increase the window size by 3x, you gain similar to what you would gain by Runahead. Of course, Runahead doesn't provide all the benefits of a large instruction window. If you have a large instruction window, you're really doing out of order execution on that window all the time, right? And you're keeping the result values. Runahead is actually very purely speculative. So it's actually discarding a lot of the values, a lot of the work that you would do in a large instruction window and not discard. Right? So there are some cases where the large instruction windows are much better, for example, over here. But there are also some cases where the large instruction windows are slightly worse. Okay, this is also interesting. You could apply this idea on in-order processors, state-of-the-art, or out-of-order processors. And you would get benefits, as you can see. In-order processors benefit more. It's about 39%, 40%. And out-of-order processors benefit less because out-of-order processors clearly have more tolerance to memory latency, right? Because they have an instruction window. They could tolerate the latencies better. This is using the same prefetcher configurations, etc. It's also good to look at in-order baseline, out-of-order baseline over here on average across these workloads. So you see that there's a big difference between in-order and out-of-order. That's the benefit of out-of-order execution in general. Granted, this is not a very fair comparison because in-order baseline was not optimized for code, etc. Okay, so this is interesting. This is an idea that was implemented in some processors. This is a talk from Sun Microsystems. They were building the Sun Rock processor until they got bought by Oracle, which really killed all of the processor design of Sun. I don't think Oracle designs processors anymore, which is bad in general for the world. But basically, this is a nice analysis that they've done, which shows that if you have a 512 kilobyte cache on these commercial workloads that they evaluated Runahead on, Scout is essentially their Runahead, they get about 40% better performance. They have an in-order processor, which is similar to what we had. So our results were actually quite similar, even though the workloads are different. That's interesting. I still take credit for the similarity of the numbers. Fine, I'm joking. But there's another thing that they also say is if you include this sort of prefetching feature, you can reduce the caching that you would otherwise have to add. So for the same performance level, if you want your performance level to be, let's say, I don't know, 1.75 instructions per cycle, using Runahead with a much smaller cache is equivalent to using no Runahead with a much bigger cache. So you can actually save 12 megabytes of cache. You could populate it with more cores. So essentially, you could save a lot of space if you think about it. And at a lower performance level, you would save less cache, but still a lot of cache, 7 megabytes. This is, I think, another example showing that how ineffective caching is. Even though it's effective, it's very inefficient. It's wasting a lot of resources. And this goes back to all of those memory-centric lectures. Right? I've shown you pictures of those caches. And I think there's a lot of proof for that. Right? Runahead execution that keeps doing Runahead is much more efficient in terms of hardware, as these folks show. So basically, effective prefetching can improve both performance and reduce hardware costs at the same time. Okay, so this is the paper. It's going to be one of your assignments. This is the Sun Rocks paper that talks about how they did it and the results. This is actually how they took it to the next level. So Sun folks were actually doing very interesting work before they got bought by Oracle. And they were actually extending this paradigm so that they could reuse some of the results. They could do Runahead for a much longer time. So they would actually use one thread context for the main program. They would use another thread context for the Runahead thread. And they would keep doing essentially this sort of processing. Runahead thread is staying ahead of the main processor. And they had a lot of interesting optimizations. But this all died because, yeah, you know what. So IBM also implemented this actually and compared Runahead execution with conventional data prefetching. This is an interesting workload analysis paper if you're interested in reading it. So you can see some results over here, which is nice. NVIDIA also, when they were doing more, let's say, their own ARM processors, experimented with this sort of feature, which is nice. And they talk about how much benefit they get. I like some of these quotes over here because they actually explain things nicely. That's the beauty of a concept. Like, I think Runahead is a very clean concept. But this is actually fascinating to me because these were better than my own results. Runahead complements the hardware prefetcher because it's better at prefetching non-strided streams, and it trains the hardware prefetcher faster than normal execution to yield a combined benefit of 13% on Spec in 2000 and up to 60% of Spec FP 2000. I think these were better than my results. Yeah. Okay. Okay, so you could enhance this. Clearly, we've discussed a bunch of downsides. So we have tried to make it much more efficient without losing the performance benefits or while increasing the performance benefits. And you can look at that. We tried to parallelize the cache misses over here. We tried to get rid of being on the wrong path as much as possible. I like this idea over here. And I think it's good to develop some creative ideas. I think this idea is very creative, but it's very hard to make it work in real life. This micro paper shows that. The idea is basically, if you're on the wrong path, you're more likely to encounter some unusual things or illegal things. For example, if you encounter a null pointer dereference, the likelihood that you're on the wrong path is almost 100%, or otherwise you have a bug in your program. Right? So that's one example. So there are other examples. If you're seeing lots of TLB misses, the likelihood that you're on the wrong path is higher than the likelihood that you're on the correct path. It's interesting. So there are a lot of other things like this that you can take a look at. Okay, we looked at a lot of these things. I think I've said some of these things, basically, energy and efficiency. So basically, limitations of the baseline Runahead mechanism is you can execute a large number of instructions without getting benefit or while getting not enough benefit. And we tried to solve that problem. I think some of the implementations, like NVIDIA implementation, actually uses this sort of Runahead as opposed to like vanilla Runahead. In fact, they cite this paper also. For pointer-intensive applications, you have ineffectiveness, but if you can predict the address of some of these instructions, you can actually prefetch dependent cache misses, so which is good. This is also an interesting idea that I'm not going to talk about. I'd encourage people to generate new ideas in general. That's always a good thing. I've already talked about these wrong path events, which is also interesting. And I will talk about limited Runahead distance, because this is actually a fundamental issue. This tried to also limit that, but in a reactive way. Here, we're going to do something proactive about 10 years later, let's say. And the problem is Runahead ends when the miss that caused it returns. You could clearly solve this problem by using another context. And we're going to use another context over here in an intelligent way, in a more memory-centric way also. Okay, so these are some papers that I'm not going to cover. You can find a lot of information in them. Let me talk about this paper that I kind of promised. So continuous Runahead. You can guess what this is, right? Continuously, you're in Runahead mode. And in fact, the memory controller is in Runahead mode. And the memory controller keeps doing Runahead and providing stuff to the processor. That's why it's memory-centric Runahead. So the motivation was, at least the vanilla Runahead covered only a small fraction of Runahead reachable misses. This depends on the configuration, of course, but in one configuration, it's like that. Because Runahead execution interval is very short. You get, on average, 60 cycles in some processor configuration. A reasonable one. This is because Runahead ends after the miss that caused it is serviced. And this is the Runahead interval distribution. You can find that information. Okay. So the key idea over here, as I said, is keep Runahead going even after a long latency cache miss is serviced. The idea actually is complemented with multiple things. We identify chains of instructions that lead to long latency cache misses based on some prior work. And we keep executing each chain of instructions in a loop in Runahead mode using some specialized Runahead execution hardware. You could do this on the processor side, but we decided that you would implement this continuous Runahead engine in the memory controller because it's much better there. You don't go through the processor, clearly. And you stop executing a chain after a fixed number of instructions. You could also do that with some confidence mechanisms, etc. But in this paper, we examine a fixed number of instructions. And the key results are quite encouraging. Essentially, you would cover 70% of Runahead reachable misses as opposed to 13%. And you get a lot more performance gain over the best Runahead implementation, which is not the vanilla Runahead, which is some other Runahead that I will not talk about, which is the Runahead buffer and some policy on top of that. And we compared to a bunch of different prefetchers over here, as you can see, and you can find more information in the paper. So I like this idea also, clearly. This is really, in my opinion, Runahead done much better. But I believe there needs to be more works in this area. And the good news is I think there are some people who are doing work. And in fact, there was a paper at Micro 2024 that builds on this work, right? That is not in these slides. Because Rahul was too busy to add that particular one, or maybe he didn't want to add that one, I don't know. But basically, the idea over here is, and this got the best paper award at Micro last year, The idea is to actually vectorize the scalar operations inside a loop to generate many independent loads at once and proactively prefetch those vectorized scalar operations. So essentially, do run ahead in a very parallel way, right? You have a bunch of scalar operations that could actually be vectorized, and you do that vectorization purely in hardware and proactively prefetch in run ahead mode, let's say. There are actually other interesting ideas that I don't want to talk about here. Any questions? So hopefully I've given you something that I've done a long time ago and I still like. Yes. Yeah. No. You mean pre-execution based thread construction that I mentioned? Yeah. Okay, that's a very good question. Yeah, I guess you don't see as many papers on like non-run ahead type of pre-execution approaches. That's correct, right? I haven't seen as much, which is interesting. I don't think it got dropped, but maybe it's not as hot of a research topic as it is. That's not necessarily a good thing, of course, you know. I mean, clearly Runahead is going still as a research topic. There are multiple groups working on Runahead, which is good. But I wouldn't say it's dropped. Maybe it's not, maybe it fell out of favor as a research topic. Somebody should do it for machine learning and then it will become interesting, right? How to accelerate LLM decoding using pre-execution thread construction. I think it's possible because that's also a quite serial process, right? Next token prediction, etc. Okay, I'm partly joking because I think there's something there, Frank. I'm not completely joking over here. Yeah, and with every word, there's always some truth in any joke, right? As Freud would say. Okay, so a run-ahead execution is really an execution-based prefetcher. It's a specialized type. But I'll go through these slides very quickly, actually. We pre-execute a piece of the pruned program solely for prefetching data, right? It's not a pruned program in what I described, but there are actually other works that I didn't describe that try to prune the run-ahead execution, what happens in run-ahead execution also. The idea of run-ahead, well, sorry, this was the idea of an execution-based prefetcher. This is the idea of run-ahead, pre-execute the main program solely for prefetching data. It's essentially the same thing, right? You can think of advantage and disadvantage of run-ahead versus other execution-based prefetchers. Run-ahead is very frugal. That's one advantage. Disadvantage, I think you kind of also seen, right? But we try to overcome some of those disadvantages with later works like continuous run-ahead. Continuous run-ahead is kind of like a thread that you create in hardware that does somewhat like run-ahead using the main program. So it's kind of in between run-ahead and this thread construction-based prefetching. So I think these questions are actually partly answered. You can make run-ahead better by pruning the program portion that's executing run-ahead mode, and continuous run-ahead is actually a very good example of this. And you can also do other things like vectorizing your scalar memory operations, like we have seen with the decoupled vector run-ahead. So one thing I will mention is taking advantage of pure speculation. This is actually nice. I think run-ahead mode is purely speculative. The goal is really to find things that you can improve the stall time later on. How do you achieve this goal most efficiently and with the highest benefit? It's still a good question to ask. And one idea is to find and execute only those instructions that will lead to cache misses. And I think there's more work to be done in this area. I don't know the full answer to this how. People have tried it, but there's more to do. So let me finish execution-based prefetching with pros and cons. I did run-ahead pros and cons, but now let's go to the outer loop, because run-ahead was an inner loop of the execution-based prefetching. Now we'll go to the outer loop and cover execution-based prefetching and finish that. Essentially, the beauty and the promise of execution-based prefetcher is you can prefetch pretty much any access pattern, which is nice. Still, you may not be efficient in any access pattern. If you have a stride that you can predict nicely, use your hardware stride-based prefetching. It's much cheaper to do that. It's very hard to beat that. But the problem is, do you have strides that you can predict very, very nicely, right? In some cases, you do actually. It can be very low cost, like run-ahead execution, for example, especially if you use the same hardware context. The reason is processor is equipped to execute the program anyway. That's what you're doing. You're executing the program except speculatively. It can be very bandwidth efficient. Runahead execution is another example over here. But that's true for a lot of other speculative thread construction mechanisms also, because they're really computing to get the address as opposed to trying to get ahead of the processor with some pattern matching mechanisms, which may or may not be as correct. Now, the downside of all execution prefetchers, based prefetchers is they depend on branch prediction accuracy and possibly value prediction accuracy, and mispredicted branches that you execute that are dependent on missing data throw the thread off the correct execution path. That's true for mispredicted values also. So if you want to actually reduce the thread, you may want to do a lot of prediction, and that prediction may go wrong. It can be wasteful because you actually speculatively execute instructions, and you may speculatively execute many instructions, as we have seen with Runahead. So energy is an issue potentially, especially using another thread context. Energy becomes a bigger issue. If you're using many thread contexts to actually do speculative pre-execution, then it becomes an even bigger issue. So who said that you just do it only on one thread context, right? Why not use 99 other thread contexts to do prefetching for one core? That's what multi-core processors are useful for in the single thread world. That's true. If your program is not multi-threaded, your multi-core processor is essentially useless, right? Or you can do multi-workload, but that's a different thing. You can occupy a separate thread context, as I said. And there's also a complexity in deciding when and what to pre-execute. So this is somewhat similar to prefetching, but there's complexity still. Okay, let me see. Maybe I'll ask you the same question. Do we continue and cover the rest of the slides, which are not going to be that much, or do we take a break for 10 minutes? Thoughts? Who says continue? These are the Runahead people. Who says stop and take a break? Why don't you guys raise your hands if you think that way? Maybe nobody thinks that way. Who says stop the lecture? We'll continue next week. Okay, I think I'll continue. I'll go through some of these things relatively quickly because this is based on my experience. And actually, at the time, early 2000s were a very different world than 2020s. Today, a lot of the work in architecture, downside or upside, I don't know. I'm not going to take it, let's say, a side over here. Like there were times in architecture where things were a lot more idea-driven. And I think of the early 2000s and late 1990s like that. Today, we're more workload-driven. In a sense, a lot of the techniques are very similar, and you apply it to different workloads. Whereas fundamental ideas are maybe reducing. I don't know if this is because we've advanced too much, or maybe our focus has shifted a bit unnecessarily to just workloads. It's good to think about that. So, but at the time, in early 2000s, there was a large focus on increasing the size of the window. And what the reason we designed Runahead actually was to counter against that trend, if you will. People wanted to design bigger, more complicated machines. And Runahead was really a different way of thinking, in my opinion. The goal was to really keep the out-of-order core simple and small, and don't use it to do something inefficiently, meaning tolerate very long memory latencies. At the expense of some benefits, of course, non-memory related, because larger instruction windows are good for example, long latency floating point operations that are dependent on each other as well. Long latency, short cache misses that are dependent on each other as well, right? But you could potentially do Runahead. So our idea was to really use aggressive automatic speculative execution solely for prefetching, which was different at the time. And this was synergistic with prefetching and branch prediction methods. So in the end, a lot of interesting and innovative ideas ensued. And it's good to see that they're also ensuing. Like it's good to see actually Micro 2023 best paper to be a Runahead paper. That makes me happy. There's also other papers that are happening. So I should also say that while we were doing this work, we discovered other papers that did an early version of Runahead, which is actually very interesting, which I don't think got a lot of credit. Maybe because they used, let's say, a small baseline, like a maybe 5-stage pipeline. But they should get credit, I think. This paper actually we discovered while we were doing the work. They did this in an in-order pipeline. So they didn't do a lot of the things that we had done in the out of order, but I think the basic idea is very similar. So we had actually called our mechanism scratch mode execution before we renamed everything to Runahead after the discovery of this paper. Because what you're really doing is scratching everything that you in this mode. So our all of the code that I've written is SME. But in the paper, everything is Runahead because we discovered this paper because this is really Runahead. So it's good to build on prior work. This is another work that we were aware of. We didn't discover it after the fact. This was before the fact. This is actually a beautiful paper. It's a one-page paper. The whole paper is here. It's actually a presentation. Astros used to have these wild and crazy ideas session, which actually had fundamental ideas before. Maybe it still has it, but maybe it's not as fundamental anymore. But basically, this Andy Glue, who's a very interesting architect, he proposes basically we should really be exploiting MLP and forget about ILP techniques. And Runahead was kind of an incarnation of that, right? You create this mode, you execute in this mode such that you just prefetch data. You're not getting any instruction level parallelism benefits. You're executing a lot of instructions, but you're not saving the results anywhere. But your goal is to really get memory level parallelism. And he has a bunch of other ideas over here that may actually lead to some other interesting things. Some of them have been exploited, like very large instruction windows that we wanted to avoid. Okay. Maybe you kind of lost the battle though, in the sense that if you look at today's processors, they have huge instruction windows. Maybe the instruction window size is 600 or so. You can correct me, or maybe even larger. I don't know. In some cases, how much is it? Yeah. Okay, there you go. 600, etc. We wanted to avoid that. So architects over time figured out how to make large instruction, how to design large instruction windows to be much more efficient. I don't completely believe that. I think there are some parts of the window that are extremely difficult to design. It comes at very high complexity, like load store queues, memory dependence prediction. All of those are extremely difficult to design. Yet architects did it so that they could tolerate it. As opposed to, this is another example of an idea that could be disruptive, but you need to rethink how you design the core. And that's what the Sun guys were thinking. The Sun Rock folks were actually doing that, in my opinion, until Oracle bought them and killed their innovation. But the mainstream companies like AMD, Intel, Apple, they all went through designing a large instruction window because that is what their expertise is in. I think the call they made is they actually examined Runahead multiple times in their designs. They may be using partially parts of the Runahead paradigm, but they're still designing large instruction windows. And then one of the main reasons is it's business as usual. We know how to do it. It's much harder to do something different that will disrupt the core design, right? So that mentality is everywhere. So it's good to keep that in mind. This doesn't mean that Runahead was not influential. So this actually won the Test of Time award. So I think I presented some of these slides. I think microarchitecture research, especially memory part of the microarchitecture, is critically important. And I think this is fun and impactful. It's harder, perhaps, but we should still do it. And this was a nice industry-academia collaboration. We worked nicely with Intel with this. So I think fundamental problems will always remain fundamental. That's one of the reasons I have this prefetching lectures. They will require fundamental and creative solutions. For example, another lecture that we're not going to have in this course is branch prediction. You can go to DDCA and look at my lectures over there. That's another fundamental problem. Much more difficult problem, I think, because the bar is much higher over there. But that means if you come up with a creative solution, that could actually be adopted more easily. Right? Everybody's doing machine learning accelerators. So you have competitors, like 1 million competitors in the world. And everybody's tweaking this part of the systolic array and that part of the systolic array and this part of the systolic array, this part of the SIMD engine, that part of the SIMD engine, doing compression, quantization, etc., which is interesting. But what are we missing is the key question, right? If most people are focusing on one problem, then we have a problem in general. We have a bigger problem. So it's good to have diversity in general in research topics. Okay, it's good that actually microarchitecture is happening right now. So this is the citation for the Test of Time award that we received, which I agree with, which is nice that somebody else recognized also. I'll let you read it. I'm not going to talk about that in general. But I would say that follow your passion. This is one of the reasons I followed my passion, actually. There were actually quite a bit of criticism that we received. Even though our papers got accepted, one of the criticism we received was, this is not a good way of designing out-of-order machines. Just build larger instruction windows. And a lot of people at Intel were doing that also. And they had some papers, a lot of complexity. If you read those papers, there's a lot of complexity in it. So existing processors have that complexity, which I don't like in general. So think about sustainability, energy efficiency, all of those get swept under the rug in a sense, right? So today people talk about sustainability. I actually gave a talk yesterday in a sustainable AI workshop here. I talk about sustainable AI. Basically, I said that if we want to talk about sustainable AI, we should first start with the basics of how we build processors. If they're wasting a lot of energy and sustainability, then what are we doing? Right? And the core principles of existing architectures waste a lot of energy and a lot of area, which is part of an equation for sustainability, right? If you actually create a lot of area, if you actually use a lot of area, a lot of resources, and a lot of power to power a processor, then you have a problem with sustainability. Anyway, basically be resilient. You will get criticism. Your focus should be on learning and scholarship in general. And in the end, quality of your work defines your impact. So I'm happy to say this, of course, after the fact. But I believe currently, like with memory-centric computing work, we're facing similar things. But I believe in that, and the goal is to do quality work over there. Okay, there's more on Runahead execution. My thesis is actually a lot more, but I'm not going to cover that. And there are clearly things over here. So let's see. Well, why do we have this? Okay. Any questions? Otherwise, we're not going to cover instruction prefetching in the last 9 minutes, probably. But you can ask questions about things we've covered, and we're going to leave off instruction prefetching for the next lecture. I wanted to add instruction prefetching. We didn't cover in the past, but I thought it was important to cover it. So we're going to do it in the beginning of the next lecture. Okay, I don't hear any questions. Yes, there you go. Yeah. Yeah. So there are several things I would say. They may do it, but they don't admit it first. But they still build large instruction windows. And the second thing is they don't need to justify anything. Because if you think about it, this is all their internal design. And they make a lot of design choices in their architecture. And none of those need to be public from their perspective, clearly. Internally, they may actually find benefits. And I actually know that people have found benefits from Runahead. But that may not justify the cost of like redesigning some of the parts. Because you want to get benefits in multiple workloads. And Runahead is great at getting benefits of long memory latency workloads. But some other workloads, you still want some of the large instruction windows. So there's some limited Runahead that happens, actually. IA64 actually had some limited Runahead also, but IA64 also died for other reasons. So in the end, I think there's no transparency to this process because these are profit-making companies, and some of them make the highest profits in the world. Well, one of them, not some of them. So they don't justify anything. Unfortunately, they don't disclose much also, meaning they don't even disclose what they do, right? Let alone what they decided not to do. If you want to figure out what they do, you usually need to be a hacker, do reverse engineering, and there are people who do that. You can discover some things that way. But that's how it is. There used to be a time when companies, especially Intel and IBM, talk about what they do in the microarchitecture, but people have become a lot more secretive recently, which is not great for the progress of humanity, which is our basic principle. But progress of humanity has always had a tension and trade-off with making money. That's a fundamental trade-off. Maybe we can end it here. If you can solve that fundamental trade-off, good luck. Sure, you're welcome. Okay, I think we're done. I'll see you next week. Have a good weekend.